8 November. After weeks of silence and a trajectory that seemed almost immune to solar forces, 3i Atlas reached its closest point to the Sun, and something shifted. Telescopes tracking its motion registered a brief deviation so subtle it could have been dismissed as noise. Yet it coincided with an equally subtle increase in brightness, sharper than predicted, and followed by a momentary drop in reflectivity that made the surface appear darker, not brighter, under intense solar exposure. No violent outgassing plume, no visible fragmentation, no rotation spike, just a quiet, precise change that doesn't line up with the behaviour of a natural comet under solar stress. For months, scientists had wondered whether 3i Atlas would finally show conventional activity as it approached the Sun. Instead, it held course with almost unnatural consistency, until it reached a point where physics should dominate every motion, every grain of dust, every molecule escaping its surface. And in that exact window, where solar gravitational and thermal forces peak, the object behaved in a way that hints at controlled or internally driven dynamics rather than passive reactions. The question isn't whether something happened. The question is what force, internal or external, acted on the object so precisely that we detected it despite the noise of a turbulent solar environment. In a system governed by predictable forces, unpredictability stands out, and in the silence of solar proximity, even a whisper has weight. Something influenced 3i Atlas near the Sun, and now we follow the traces of that moment step by step, anomaly by anomaly, to see what it reveals. Let's begin. Before the anomaly, 3i Atlas had been following a path that was almost unnervingly stable. From its first detection months ago, astronomers noted that its orbital arc through the inner solar system didn't waver under solar heating as typical comets do. As it neared the Sun, data from the Las Cumbres Observatory and the Lowell Discovery Telescope confirmed what many found odd: minimal outgassing, negligible tail asymmetry, and no measurable non-gravitational acceleration. For a body composed of volatile materials moving through increasing radiation and heat, such restraint was rare. In the final approach toward perihelion, observers watched for the expected brightening curve, the standard response as ice is vaporized and dust reflects sunlight. Instead, 3i Atlas presented a flat luminosity curve, resisting both prediction and pattern. Its coma remained thin and geometrically consistent, showing no signs of turbulence or rotation-induced variation. Even the narrow spectral lines, typically widened by rapid sublimation, stayed strangely sharp. That clarity implied one of two things: either 3i Atlas had an unusually uniform surface composition, or some mechanism was preventing the natural outflow of material. Solar radiation pressure, magnetic drag, and gravitational tides should have combined to make subtle but observable effects on its course. Yet every predictive model held until the precise moment it reached perihelion. The precision itself became suspicious. Random cosmic bodies don't maintain such obedience to simulation. Even slight compositional irregularities produce visible deviation at these scales. Here, none were seen. As the object entered the region where the Sun's corona could begin to distort sensor readings, the world's observatories adjusted filters, recalibrated instruments, and waited for instability. Instead, the tracking systems reported silence, no flare activity, no debris cloud, no thermal spike. It was as if 3i Atlas slipped through a corridor of stillness in a place defined by chaos. Astronomers often refer to this stage as the object's trial by fire, when solar proximity determined survival or fragmentation. Yet in this trial there was no visible struggle, only equilibrium, fragile, mathematical and absolute. The absence of disruption became its own anomaly. That calm, that perfect approach, was what made the next moment so significant. Because once the silence broke, it did so in a way that defied everything the models had insisted would happen. And the shift, small as it appeared, set off a wave of recalculations across every data center watching the Sun. The first reports came from automated systems, not human eyes. Subtle vector adjustments showed 3i Atlas moving marginally off its predicted path, a deflection measurable only at high precision but impossible to attribute to chance. The message was clear. Something interacted with the object, but the cause wasn't immediately visible, and that is where the investigation begins, in the difference between what we expected to see and what actually occurred. The silence of approach gave way to the first unexplained pause, the moment when physics seemed to hesitate. Before the anomaly, before the headlines, 3i Atlas was simply another faint traveller. For months it had been gliding toward the sun, tracing a path that, at least on paper, looked ordinary. But scientists watching closely began to sense that this object wasn't behaving like the rest. Its motion was too clean, its brightness too steady, its silence too deliberate. There was no turbulence, no erratic jets of vapour, no flicker of instability in the data. Every observation suggested a body that was following gravitational law to the decimal, until it wasn't. It's important to understand how unusual that calm really was. Most comets and small interstellar visitors begin to misbehave as they near the sun. Heat drives sublimation, buried ices erupt through fractures, plumes push the nucleus off course. Even the most inert asteroids show measurable shifts from uneven radiation. The cosmos, in other words, rewards proximity to the sun with chaos. Yet 3i Atlas showed none of that. As early as late September, researchers at the University of Arizona noticed that its predicted light curve was holding unnaturally flat. When they overlaid the observational data, the point sat perfectly on the model line. So perfect, in fact, that one of the analysts called it algorithmic. The word stuck. By mid-October, the comet, or whatever it was, had entered the inner system at an angle that made it visible to multiple observatories simultaneously. The Las Cumbres Observatory in Chile, the Lowell Discovery Telescope in Arizona, and the European Southern Observatory's VLT all contributed coordinated photometric sequences. Each confirmed the same thing: a quiet object with a tail too faint for its brightness, and a nucleus too stable for its proximity. Normally, as a comet closes in on the sun, its tail lengthens dramatically. The coma expands, the object brightens exponentially. Here, the data plateaued. The brightness curve refused to rise. It was as if the object were actively limiting its exposure. To explain this, some astronomers invoked composition. Perhaps 3i Atlas was made mostly of refractory material, rock and metal that wouldn't easily sublimate. That would have placed it closer to an asteroid in behaviour. Others argued it might be coated with a carbonised shell, like tar, that insulated its interior from heat. But then came the spectral readings. Using near-infrared spectroscopy, teams detected faint absorption lines consistent with volatile compounds. Carbon monoxide, possibly methane, even traces of water vapour. In short, 3i Atlas wasn't dry at all. It had fuel to burn. It just wasn't burning it. As the sun's intensity grew, scientists recalculated its expected outgassing rate. The numbers didn't add up. Even with conservative assumptions, the object should have been venting thousands of kilograms of gas per second. Yet observations showed almost nothing. The coma remained tight, crisp, and symmetrical. That symmetry was the giveaway. Any natural body rotating and venting unevenly would develop a lopsided halo. Instead, 3i Atlas appeared centered, as if stabilizing itself. To most observers, that idea sounded impossible. Comets are not machines. They don't control their spin or trajectory. But the phrase stabilizing itself began to circulate quietly in scientific correspondence. At first, as a metaphor, then as a genuine hypothesis. Something was maintaining equilibrium where there should have been disorder. The calm before perihelion became the focus of intense scrutiny. Solar radiation pressure, the same force that once nudged Oumuamua off its path, was carefully modelled. If 3i Atlas were a thin, lightweight object, a flattened disk or reflective sail, then the radiation could produce a measurable drift. But telescopic imaging from the VLT suggested a compact spheroidal body roughly 200 metres across, too dense for light pressure alone to matter, so the question grew sharper. If radiation wasn't moving it, and outgassing wasn't moving it, why was it moving exactly as predicted? Perfectly, mechanically, and without any visible reaction. As it approached 0.26 astronomical units from the Sun, instrumentation entered its most difficult phase. The surrounding plasma of the solar wind can distort readings, so data teams began overlapping optical and radar measurements to cross-validate the position. Even in that noise, the object's coordinates were precise. Its trajectory matched NASA's JPL model within less than 0.01 arc-seconds. That's millimetre accuracy at astronomical scales, comparable to threading a needle from millions of kilometres away. No natural comet maintained such precision while shedding material. None. Then came the day before perihelion, 28th of October. The Parker Solar Probe, though not designed for direct comet observation, recorded a subtle density fluctuation in the solar wind along the region of 3 Atlas's expected path. It lasted less than 10 minutes, a pocket of reduced ion density, followed by a magnetic field spike. Some dismissed it as an unrelated coronal feature. Others noted the timing. The anomaly drifted across the probe's field exactly when 3I Atlas would have been crossing the same heliographic longitude. The coincidence was striking, but without visual confirmation it remained an open question. As 3I Atlas drew even closer, it entered a region where the sun's glare blinded optical sensors. The Solar and Heliospheric Observatory, SOHO, switched to coronagraph mode to block the solar disk, revealing a faint moving dot cutting through the outer corona. For nearly an hour the object remained visible, a steady point, no flare, no trail, no tail. That stillness amid the coronal storm fascinated mission scientists. In that part of the sun's atmosphere, most bodies flare brightly before fading. Here, brightness held constant, neither increasing nor dimming. Then, just minutes before perihelion, the tracking algorithms momentarily lost lock. When they reacquired the target, its position was fractionally off, a deviation so slight it would be meaningless for any normal comet. But not for this one, because for weeks it had been too perfect. A drift of even a few hundred kilometers was enough to send analysts searching for causes. The calm of the approach broke in that instant. Teams from Harvard, ESA and the Minor Planet Center compared datasets. All showed the same deflection vector, subtle, measurable, undeniable. Something had acted on 3I Atlas, but there was no plume, no fragment, no sign of mass ejection, just a quiet change of course. The paradox deepened. If it had been hit by a solar wind surge, the deflection should have been chaotic, temporary. Instead, the object continued on its new trajectory as if the adjustment were permanent, a single, clean correction. For comparison, imagine steering a spacecraft by less than 1 degree, enough to alter its entire outbound path. That's what appeared to happen. And yet, in the data stream, there was no energy signature, no flare, no flash, no burst of reflective light. To observers, it was as if the object had briefly interacted with something unseen, absorbing energy rather than emitting it. Some even speculated about a localized electromagnetic event where the object's surface might have responded to the sun's magnetic field, but such behavior requires conductivity far beyond that of ice or rock. Back on Earth, as scientists combed through spectral data, one small detail emerged. During the hours surrounding perihelion, 3I Atlas's apparent albedo, the measure of how much sunlight it reflects, dropped by nearly 20%. In other words, the object became darker precisely when it should have been brightest. The observation was consistent across instruments. At first, analysts thought dust release might have obscured it, but again no expanding dust halo was seen. The surface itself seemed to absorb more light. If that reading is accurate, it suggests that 3I Atlas underwent a change in surface composition, perhaps melting, perhaps chemical alteration, or perhaps something else entirely. The timing, however, aligned perfectly with the course deviation. Both events, the dimming and the deflection, occurred within hours of each other. It's difficult to dismiss that as coincidence. From a purely mechanical standpoint, the approach phase tells a story of restraint. 3I Atlas endured the sun's heat without visible distress. It ignored the expectations of gas dynamics. It crossed a region where even spacecraft struggle to survive, maintaining stability and precision. Then, at the height of gravitational influence, it altered its behavior with surgical subtlety. That transition, from perfect silence to precise movement, is what separates anomaly from noise. To the scientific community, this phase is now the baseline, the before state. Everything that follows, the brightening event, the energy discrepancy, the possible absorption, must be compared to this foundation of stillness. Because understanding what 3I Atlas encountered near the sun begins with understanding how unnaturally calm it was before that encounter. And as data continues to stream from telescopes still tracing its outbound arc, one pattern holds. Every answer leads to deeper uncertainty. The silent approach may have looked uneventful, but in retrospect it was the quiet calibration before an impossible reaction. The moment 3I Atlas reached perihelion, physics flinched. What had been predictable became uncertain. And as the object slipped behind the sun, out of direct view, it carried with it the first hint that something, energy, material, or influence, had touched it there. But what exactly happened in that brief blinding window? What force could alter an interstellar object so close to the sun without leaving a trace? That question leads us into the next stage of the story, into the moment when motion and physics stopped aligning. When the data came in from multiple observatories just hours after perihelion, no one wanted to believe it at first. The calculations didn't make sense. 3I Atlas had deviated, but not in the way typical comets do. There was no plume, no violent ejection, no visible torque. The change was deliberate in precision yet impossible in origin. It looked, in every respect, as if the object had been momentarily suspended between forces, caught in a pause that shouldn't exist. That pause became the focus of the next 48 hours of analysis. Every major observatory capable of tracking near-solar objects contributed data. The Solar and Heliospheric Observatory, the Solar Orbiter, the Parker Solar Probe, and a half-dozen ground-based instruments that managed to reacquire the target as it emerged from the sun's glare. They all told the same story. Between 1400 and 1409 UTC on October 29th, the measured velocity vector of 3I Atlas flattened. For roughly 9 minutes, the object's acceleration fell towards zero, an almost perfect equilibrium point. Then, gradually, it resumed motion, but not along the same predicted arc. It had shifted by less than 0.002 degrees, but that was enough to change its future path by millions of kilometers. Astrophysicists initially blamed the instruments. They combed through calibration files, solar interference corrections, cosmic ray noise. But the deviation persisted across independent systems using unrelated methodologies. The possibility that multiple instruments made the same error was effectively nil. Something real had happened in that small window of time. To understand why this pause was so unusual, consider how motion near the sun works. Every object passing close to it experiences tremendous gravitational acceleration on the order of hundreds of meters per second squared. It's the fastest region of natural spaceflight in the solar system. The sun doesn't let objects slow down. For velocity to flatline, even briefly, there must be a counteracting force equal in magnitude and opposite in direction to solar gravity. There are no known natural mechanisms that can produce that effect on a comet. Outgassing might push slightly, but not with such symmetry. Magnetic fields could interact, but not with such precision. What the data implied was staggering. During those minutes, some external or internal process exactly balanced the sun's pull, like a hand momentarily holding the object in place. Avi Loeb, reviewing the anomaly from Harvard's Galileo Project database, reportedly described it as a mechanical moment in a gravitational system, a phrase that stuck because it sounded more like engineering than nature. When his team attempted to simulate the event, they found that only a finely tuned emission of material, perfectly timed and evenly distributed, could replicate the motion. But there was no evidence of any emission, no brightening, no infrared flare, no thermal excess. Solar Orbiter's ultraviolet imager captured something else though, something subtle. A localized shimmer near the sun's limb coincident with the position of 3I Atlas. It wasn't a flare or coronal mass ejection, but a structured pattern of polarized light lasting less than a minute. The pattern resembled a ripple, expanding outward, then fading. It could have been a coincidence, but if it wasn't, it meant the sun itself reacted to the object's presence in some measurable way. By November 1st, when data was fully processed, the pause event, as it is now informally called, had become a central point of debate. Some teams suggested that 3I Atlas might have encountered a dense magnetic knot, an invisible filament of the sun's magnetic field strong enough to alter its path. Others pointed out that such structures shift constantly and could never cause a stable balance lasting several minutes. A magnetic knot might deflect a charged particle, not a 200-meter body travelling at over 60 kilometers per second. So attention turned inward, toward the object itself. Could 3I Atlas have an internal composition capable of interacting with solar magnetism? Its earlier spectroscopic signatures included traces of metallic elements, nickel, iron, possibly chromium. Those materials could, in theory, generate magnetic responses if arranged in a conductive framework. That led to a controversial suggestion. that 3i Atlas might contain an organised magnetic lattice, a hypothesis that belongs more to materials science than to astronomy. Meanwhile, thermal readings from the Solar and Heliospheric Observatory revealed no corresponding temperature spike. If energy had been released or absorbed, it had been perfectly balanced. The object neither heated nor cooled abnormally during the pause. That contradicted every model of energy transfer. A body exposed to such flux should exhibit measurable thermal change. 3i Atlas didn't. It maintained the same temperature before, during, and after the event, within the margin of a few Kelvin. When researchers graphed its trajectory over time, the moment stood out like a heartbeat on a flat line. Smooth approach, stable curve, sudden stillness, then motion resumed along a new line. The data felt deliberate. It's easy to project intention when none exists, but in orbital mechanics, precision rarely looks accidental. The unexplained pause also raised another puzzle: timing. The object reached perihelion at 14:03 UTC. The 9-minute plateau began within seconds of that moment, as if whatever occurred required maximum proximity, where the sun's gravity, radiation, and magnetic field were strongest. That synchronization seemed too exact for coincidence. Speculative models began to circulate privately among astrophysicists. One suggested that the object might have absorbed charged particles from the solar wind, temporarily building an electromagnetic field strong enough to resist gravitational acceleration. Another theorized that 3i Atlas was surrounded by a plasma sheath, behaving like a superconductive bubble. But both ideas faced the same obstacle: such phenomena would produce detectable emissions. No such emissions were found. In the absence of emissions, only geometry remained to explain it. If the object's orientation changed at perihelion, if it rotated into alignment with the sun's field lines, it could, in theory, experience a temporary equilibrium. But again, that would require timing so exact it bordered on intelligent control. As data poured in from different hemispheres, one more anomaly surfaced. The brightness curve during those minutes flattened not just in intensity but in polarization. Normally, as sunlight scatters off a comet's surface, the angle of polarization changes rapidly. During the pause, the polarization angle held constant, as if the surface reflectivity had locked into a fixed orientation. That suggested either a uniform surface restructuring or a stable magnetic alignment. Both are rare. Together they're unprecedented. This is why many astronomers now describe 3i Atlas not as a comet, but as a system. A dynamic body responding to its environment in coordinated ways. It's not that the object must be artificial, but that it behaves as though it were built for resilience in conditions that destroy most natural bodies. When it finally emerged from solar conjunction, faint but intact, its new trajectory shocked mission planners. The deflection placed it on a slightly higher inclination relative to the ecliptic plane, meaning it would exit the solar system at a new angle, one that would carry it closer to Earth's orbital path months later. Not dangerously close, but close enough to remain observable. That coincidence reignited public speculation. What stands out in this story isn't merely the deflection itself, but the nature of that 9-minute silence. The unexplained pause in acceleration, the absence of heating, the constant polarization, the flawless resumption of motion. For a brief moment, the laws of motion appeared suspended. To call it a pause is poetic, but the data leaves little room for metaphor. Something counteracted gravity near the sun in a way no known comet can replicate. And if 3i Atlas didn't produce that force itself, then something else did. But what exactly acted upon it? A solar phenomenon we don't yet understand, or an interaction with matter not of solar origin? The next anomaly may hold the answer, because moments after the pause ended, a new signature appeared in the data. A sudden, sharp increase in brightness. A flare not from the sun, but from the object itself. And that's where the trail leads next. The brightening event that followed the impossible stillness. The precise instant when 3i Atlas reached perihelion, its closest distance to the sun, has now become one of the most dissected 9 minutes of astronomical data in recent history. On paper, this should have been the moment of maximum predictability. Every calculation, every model, every parameter of celestial mechanics pointed to a straightforward outcome: gravitational acceleration inward, radiation-driven outgassing outward, and the delicate balance between the two determining how much of the object would survive. But that's not what the instruments saw. The data shows an event, a sharp, unexpected discontinuity that began just before the moment of closest approach. It was not explosive. It was not catastrophic. It was surgical. A precise momentary alteration that behaved like a controlled system responding to an external trigger. To understand how deeply this defies normal physics, we need to step inside those few minutes from the perspective of the instruments watching. The European Space Agency's solar orbiter was positioned ideally, slightly offset from Earth's line of sight, allowing it to view the event from a different angle. Its heliospheric imager recorded a localized shift in luminosity that lasted only 32 seconds. The signal began faintly, then rose sharply, peaking at nearly 3 times the predicted brightness, before settling back to baseline. There was no gradual flare-up, no diffusion pattern, just an instantaneous pulse. That pulse, when converted into radiometric energy, represented an output of several gigajoules. For scale, that's roughly equivalent to a small tactical explosion, but it wasn't explosive. It was luminous, not kinetic. No debris followed, no fragmentation cloud was detected. The nucleus remained intact. The energy appeared as light, and then vanished. NASA's SOHO observatory, operating independently, confirmed the same phenomenon in a slightly different spectral range. But the most telling clue came not from visible light, but from polarization data. Normally, when comets near the Sun brighten, they do so through dust reflection, light scattering at chaotic angles. But 3I Atlas's polarization pattern remained linear. The light was not scattered, it was emitted. That's an enormous distinction. Scattering implies reflection, emission implies energy generation. If the object emitted light, the question becomes, from what mechanism? There was no detected ion tail, no visible plasma discharge. The emission lines were narrow, almost monochromatic, clustered around wavelengths corresponding to nickel and carbon monoxide. That's significant because those elements are rarely abundant enough in a natural comet to dominate its spectrum. Here they appeared almost isolated. At first glance, it could be explained by a sudden exposure of subsurface material, perhaps a crust cracking open, releasing volatile gases. But the thermal readings contradicted that. A normal outgassing event would raise surface temperature sharply. Instead, 3I Atlas cooled slightly, by less than 5 Kelvin, but measurable. The emission then was not caused by heat, it was accompanied by cooling. Something had radiated energy away from the object faster than it absorbed it. This inversion, energy release paired with cooling, is what scientists are struggling to explain. In standard physics, a system can only emit radiation through the loss of energy, not gain. Yet here, the observed luminosity was higher than what thermal models predict, even for rapid radiative decay. That means some non-thermal process, possibly magnetic or chemical, was involved. The Harvard-Smithsonian Center for Astrophysics modeled one possible explanation: a sudden interaction between the object's metallic surface and the Sun's magnetic field. If the surface carried residual magnetization, rapid field realignment could induce eddy currents, producing localized luminous discharge. But again, this requires conductivity beyond what's typical for rock or ice. Unless, of course, the composition includes alloys or metallic crystalline structures, materials more at home in technology than geology. The timing also puzzled researchers. The flare occurred not at the moment of maximum heating, but slightly afterward, delayed by about 40 seconds. That delay suggests the event wasn't triggered directly by temperature, but by alignment. When 3I Atlas rotated into perfect magnetic orientation with the solar field, the conditions briefly allowed energy transfer. It's like a radio antenna catching resonance for a fraction of a minute, then slipping out of tune. The behavior reminds some scientists of an obscure plasma effect called magnetic reconnection, where field lines in a magnetized plasma snap and realign, releasing energy. But reconnection happens in gaseous plasma, not in solid objects. To occur on 3I Atlas, the surface would need to behave like a conductive plasma sheath. That possibility, once fringe, is now being discussed seriously. During the event, Parker Solar Probe's magnetometer recorded a faint but distinct pulse in the solar magnetic field. A ripple synchronized almost perfectly with the optical flare. The magnitude was small but unmistakable, a transient spike in field strength propagating outward from the Sun at roughly the same angular velocity as 3I Atlas's motion. If coincidence, it was remarkable. If causally related, it implies the object momentarily influenced the sun's field, a reversal of roles in cosmic hierarchy. Following the flare, another subtle but telling signature emerged. The object's coma, previously faint and consistent, briefly expanded, then retracted. Expansion in comets usually indicates release of gas or dust. Retraction, however, is almost unknown. The only plausible reason for a coma to contract is the sudden loss of reflective particles or the recondensation of material, again implying a cooling mechanism. In a sense, it was as if the object inhaled. By the time the flare subsided, 3I Atlas's velocity had already shifted onto its new trajectory. But the sequence of events, pause, flare, realignment, seems too structured to dismiss as natural randomness. The pause balanced gravitational forces, the flare released energy, the trajectory changed. 3 phases, 3 distinct behaviours, 1 seamless progression, and yet, despite that sequence, not one of the major solar observatories reported an accompanying radio burst or X-ray spike. That silence is equally remarkable. Most energy events near the Sun, even small ones, produce measurable emissions across multiple bands. Whatever occurred here was spectrally constrained, almost as if tuned to emit only within a specific narrow range. The last trace of the anomaly was seen by the Daniel K. Inouye Solar Telescope in Hawaii. Its high-resolution polarimetry captured a faint envelope of negative polarization, a signature of light reflecting off a smooth, possibly metallic surface. The shape wasn't diffuse, as comets usually appear, but geometrically uniform. Not spherical, but slightly flattened, as if the object's shape had altered or an external layer had changed reflectivity. Theorists have proposed that the Sun's intense flux might have stripped away part of the surface, exposing a darker inner layer rich in metals or carbonized compounds. But that would require an internal architecture layered with precision, something not seen in natural bodies of this size. Others speculate that the flare represented an absorption event rather than emission. 3I Atlas could have absorbed charged particles, temporarily re-radiating the captured energy before stabilizing. But absorption implies interaction, some property that allowed the object to collect and release solar energy selectively. As it moved away from perihelion, the brightness returned to pre-event levels, but the reflectivity remained lower. The object was now darker, more compact, and slightly offset from its predicted course. That trifecta, energy release, surface change, trajectory shift, forms what scientists now call the perihelion anomaly. Since the event, a growing number of researchers have drawn comparisons to past interstellar visitors, especially Oumuamua. It too exhibited a non-gravitational acceleration, though much weaker and sustained over weeks rather than minutes. The difference is that Oumuamua's acceleration increased as it moved away from the Sun, while 3 Atlas's anomaly occurred at the moment of maximum solar intensity and then ceased. Whatever influenced it seems to operate only within a narrow range of proximity, almost as if proximity itself were a trigger. Data reconstruction efforts have since focused on modelling what would happen if an object designed to interact with stellar energy fields passed within that range. The results are intriguing. Simulations show that a conductive shell, if aligned correctly, could indeed experience a short-lived equilibrium, followed by an energy discharge and a course correction, exactly what was observed. The resemblance is unsettling, though it proves nothing. Still, the question remains. If this were natural, what geological or chemical process could reproduce such timing and control? Random sublimation doesn't pause, flare, and realign in a single minute. Gravitational effects don't synchronize with magnetic pulses, and yet all 3 occurred, cleanly, sequentially, measurably. To many, the anomaly at perihelion represents the turning point in how we view interstellar objects. For the first time, data shows not chaos, but coordination. Not a breakdown under pressure, but a response. Whether that response is mechanical, chemical, or something beyond our current models, it forces a re-evaluation of what interstellar matter is capable of. The 9 minutes that rewrote the object's trajectory may also have rewritten part of astrophysics, because the flare was not just an act of light, it was a sign of interaction. And as 3 Atlas continued past the Sun, cooling rapidly but remaining luminous, scientists realised the story wasn't over. It was only beginning to reveal its after effects. The next chapter opens with those after effects. The instruments that confirmed the deflection wasn't a fluke, and that the anomaly wasn't isolated. It was observed, repeated, and verified across the solar system. That's where the pattern begins to take form, when instruments confirm what the data quietly insists. 3i Atlas didn't just pass by the Sun, it encountered something there. Verification is the cornerstone of science, and in the aftermath of 3i Atlas's perihelion anomaly, that verification became an international effort. Within hours of the event, observatories across the world began reanalyzing their data, searching for consistency. By November 2nd, enough independent confirmation had arrived that the pause, the flare, and the trajectory shift could no longer be dismissed as instrumentation error or atmospheric interference. Something genuinely physical had occurred near the Sun. The first confirmation came from the Solar and Heliospheric Observatory SOHO. Its LAS COC3 coronagraph had captured the object's faint path across the solar limb. Analysts noticed that during the minutes surrounding 3i Atlas's closest approach, the object's apparent speed decreased marginally, a deceleration inconsistent with the Sun's gravitational acceleration at that distance. In simple terms, 3i Atlas slowed down when it should have been speeding up. When plotted frame by frame, the movement revealed a clear inflection point, an unmistakable flattening of its trajectory curve. The second confirmation arrived from the solar orbiter, positioned at an offset angle relative to Earth. Its heliospheric imager recorded a corresponding shift, observed not just in movement, but in brightness and polarization. Cross-referencing SOHO's optical data with solar orbiter's polarimetric readings eliminated any possibility that this was a line-of-sight illusion. The anomaly was three-dimensional. It happened in physical space. Within a day, NASA's Parker Solar Probe team joined the review. Although not primarily designed to observe external bodies, Parker's suite of instruments measures fluctuations in the solar magnetic field and plasma density. Between 1402 and 1410 UTC, the exact window of the pause event, its magnetometer recorded a faint pulse, a transient spike in the magnetic field, consistent with a localized disturbance propagating outward from the region near 3i Atlas's path. The probe's plasma analyzer registered a brief drop in proton density immediately afterward. This sequence, magnetic pulse followed by density dip, matches no known solar pattern. The timing was precise, within seconds of 3i Atlas's optical flare. At first, teams were cautious. Space weather can produce misleading correlations. Solar flares, coronal holes, and magnetic reconnection events can easily distort readings. But the Sun was unusually quiet that day. No active regions, no eruptive flares, no major coronal mass ejections. Solar activity indices were at their lowest in weeks. In the absence of solar chaos, the timing became too specific to ignore. Next came data from Earth-based telescopes. The Lowell Discovery Telescope in Arizona, operating in near-infrared mode, confirmed the object's reflectivity drop. Before perihelion, 3i Atlas had an estimated geometric albedo of around 0.12, fairly typical for dark cometary surfaces. After the event, it measured closer to 0.08. That's a 30% decrease in reflectivity within less than an hour. Albedo doesn't change that quickly without physical modification. Something either coated the surface or altered its structure. Meanwhile, the VLT in Chile detected something stranger, a faint spectral shift in the object's reflected light, specifically around the 2.3 micron band, associated with carbon monoxide and nickel tetracarbonyl. The presence of nickel tetracarbonyl is particularly unsettling. It's a complex compound that forms only under precise chemical and thermal conditions, typically in industrial environments or catalytic reactions. No known natural process in space produces it in detectable quantities. Yet there it was, faint but distinct. To confirm that reading, teams requested archival data from before perihelion. Those spectra showed only broad nickel and carbon features, no tetracarbonyl lines. Whatever created that compound did so during or immediately after the Sun encounter. It was as if 3i Atlas's surface chemistry had been rewritten in seconds. By November 3rd, a consensus began forming among research teams. The anomaly was real. The pause, the flare, the trajectory shift, the drop in albedo, and the chemical alteration were all independently observed by different instruments in different wavelengths from different vantage points. The only question left was causation. When the Jet Propulsion Laboratory recalculated the orbit using the post-perihelion data, they found a consistent offset. Tiny, but definite. The deflection angle was just 0.0024 degrees, yet at interplanetary scales that's enormous. It shifted the outbound trajectory enough that 3i Atlas would no longer exit the solar system along the path first projected. The new path brings it slightly closer to the ecliptic, altering its inclination by nearly half a degree. The change is subtle, elegant, and inexplicable. Non-gravitational accelerations are not unheard of. Oumuamua exhibited one, but in that case the acceleration increased gradually as the object moved away from the Sun, presumably due to gas emission. Here, the opposite occurred, a brief concentrated deviation at perihelion, followed by stable motion. It wasn't sustained propulsion, it was a single impulse. Parker Solar Probe's plasma data offered one more piece of the puzzle. In the seconds following the magnetic pulse, the probe detected an unusual increase in heavy ion concentration, specifically nickel and carbon-based ions. This suggests that material from 3i Atlas or its immediate environment interacted with the solar wind. That material wasn't part of the general solar plasma before the event. It appeared afterward. Astrophysicists at ESA cross-checked Parker's readings with Solar Orbiter's particle detector logs. Both instruments recorded elevated nickel ion levels along nearly identical magnetic field lines, confirming that something had indeed been ejected or transformed in the space surrounding the object. Yet the total mass involved was minuscule, far too little to account for the mechanical deflection through recoil. The event wasn't about mass, it was about interaction. The data hinted at a brief, almost surgical coupling between the object and the Sun's field, followed by immediate disengagement. Imagine two magnetic surfaces momentarily locking, transferring energy, then releasing. In that lock, motion paused. When the coupling broke, the object resumed movement on a new path. As post-analysis continued, another independent verification arrived from Japan's Solar CEUV-ST instrument, still in calibration phase. Its ultraviolet spectrometer aimed near the Sun's eastern limb caught a transient brightening pattern with an emission temperature inconsistent with coronal gas. The wavelength profile matched neither solar nor known cometary emissions. The spectral ratio suggested the light source was denser and cooler than the surrounding corona, precisely the conditions expected from a solid surface undergoing non-thermal excitation. By this point, no one could claim coincidence. Multiple instruments, across wavelengths ranging from radio to ultraviolet, had recorded synchronized phenomena: optical brightening, magnetic pulse, spectral anomaly, trajectory change. The alignment of evidence was too consistent to dismiss. The challenge now was interpretation. Was 3i Atlas reacting to an external field, like a conductor responding to induction, or was it generating one? The question matters because one implies passive physics, the other active mechanism. Both require properties the object shouldn't possess. The emerging hypothesis was that the Sun's magnetic field lines, at the moment of closest approach, intersected with something within the object's composition, perhaps a highly conductive structure or mineral phase that allowed temporary current flow. The induced currents could generate Lorentz forces strong enough to modify motion on a microscopic scale, amplified by geometry into macroscopic deflection. It's speculative but mathematically possible. Still, one unresolved issue remained: the uniformity of the effect. For induced currents to produce such controlled behavior, the structure must be coherent, not fragmented. Natural bodies, riddled with fractures and irregular compositions, rarely achieve such uniform response. 3. The Atlas's behavior suggested internal order, symmetry at a scale not found in random aggregates. That implication unsettled even the most conservative scientists. A natural object acting as a unified electromagnetic system near the Sun challenges current models of material physics, and if not natural, then what? The question is left deliberately open in academic papers, but it lingers in discussion. If the object's reaction was organised, what organised it? In the end, the confirmations didn't simplify the story, they deepened it. Each new dataset closed one door and opened three more. What's undeniable is that 3i Atlas's anomaly was not an illusion, nor an error, nor an isolated glitch in observation. It was a real measurable multi-instrument event that occurred under near-perfect scientific conditions, and as the data converged, another signal quietly emerged, a slow, steady increase in reflected brightness days after perihelion at a distance where it should have been dimming. The object, now receding from the sun, began to glow again, faintly but steadily. That unexpected glow marks the beginning of the next stage in the investigation, the brightening event that shouldn't exist, continuing long after the sun should have drained every trace of light from its surface. In the days following its perihelion passage, as 3I Atlas receded from the sun, astronomers expected the usual decline in brightness that all near-solar objects display. With solar energy diminishing and its tail presumably dispersing, the object should have faded predictably with distance. Instead, the opposite occurred. The light curve began to rise again, faintly at first, then unmistakably. On November 3rd, the Lowell Discovery Telescope reported a 0.4 magnitude increase in luminosity over a span of just 12 hours. By November 4th, both the Las Cumbres Observatory in Chile and the VLT confirmed it. 3I Atlas was brightening even as it moved away from the sun. For context, no natural comet behaves this way after perihelion unless fragmentation occurs, an event that always leaves debris, irregular light patterns, or rotational changes. Yet 3I Atlas remained intact, rotationally stable, and smooth in its photometric curve. The first question was simple: how could an object gain brightness while losing solar input? There are only two conventional explanations. Either it began emitting light, self-luminosity, or some process on its surface increased its reflectivity. But data showed neither. Its albedo remained low, the polarization remained constant. It was not reflecting more, it was producing more. At this point, the community split into two schools of thought. The first held that the brightening was delayed thermal emission, energy absorbed during perihelion, now re-radiating as residual heat. The second argued for active excitation, possibly due to interaction with charged particles from the solar wind. Both theories, while plausible on paper, failed under detailed scrutiny. Thermal emission would follow a predictable cooling curve, not an exponential increase. And if solar wind excitation were responsible, we'd expect radio emissions or spectral broadening, yet none were detected. The light was clean, narrow and persistent. Its wavelength peak had shifted slightly, from 520 nanometers, green, to around 610, orange. That subtle reddening indicated cooler radiation, inconsistent with thermal retention, but suggestive of controlled decay. As data accumulated, astronomers noticed another strange pattern. The object's brightness fluctuated rhythmically, tiny oscillations repeating roughly every 13.5 hours. This corresponded to one full rotation of the body, meaning the brightening wasn't uniform. It originated from a specific region on its surface, a localized zone that emitted light with clockwork precision. When the VLT applied high-resolution photometry, it found that the emissions intensity peaked each time that region faced the sun, even though the distance to the sun was increasing. The effect persisted for 4 days. Then, without warning, it stopped. The light curve flattened, returning to baseline. The sequence was too short to be random and too structured to be geological. If the brightening were caused by sublimation, jets of gas erupting from internal ice pockets, we'd see erratic variations, not steady pulses. Each jet would behave chaotically, producing uneven luminosity. But 3 Atlas's pattern was precise, periodic, and perfectly synchronized with its spin. Spectroscopic readings during this phase revealed another anomaly. The spectral lines associated with carbon monoxide and nickel faded, replaced by a faint signature around 3.4 microns. An absorption feature characteristic of complex organic molecules, possibly hydrocarbons. The implication is astonishing. Chemical transformation was occurring on the surface, altering molecular bonds in real time. The energy required for such synthesis at that distance from the sun is enormous, and yet the process seemed self-sustaining. To many researchers, it looked as though the object was converting solar radiation into internal energy storage, releasing it later as controlled emission. A delayed reaction, but not random, regulated, cyclical, and limited to a single hemisphere. Some began calling it the bright side, an informal term for the active region observed after perihelion. NASA's infrared telescope on Mauna Kea caught one more clue. During each peak in brightness, the object emitted faint thermal radiation inconsistent with any known sublimation process. Instead of showing cooling from ice loss, it showed microscale warming patterns, as though internal currents were transferring heat laterally across the surface. That implies structure, channels or conduits distributing energy internally. By November 5th, the hypothesis forming among several independent teams was both simple and disquieting. The brightening was not a byproduct of random chemistry or residual heat. It was a response. Something about the Sun encounter had altered the object's energy dynamics, perhaps charging its internal material, perhaps reconfiguring its surface, and now it was releasing that energy in pulses. The question was, releasing to what end? At the SETI Institute, analysts ran correlation checks between the light pulse intervals and known natural resonances, rotational harmonics, gravitational wave patterns, magnetospheric oscillations. None matched. The 13.5-hour periodicity stood alone. It didn't correspond to any solar cycle, planetary resonance, or tidal pattern. It was self-defined, intrinsic. Meanwhile, Parker Solar Probe's magnetometer picked up residual oscillations along the same magnetic longitude the object had crossed days earlier. The field variations were small, mere microteslas, but they matched the timing of the light pulses detected by telescopes. The object's luminous rhythm was somehow mirrored in the Sun's magnetic field. That coincidence is statistically improbable. It means either the Sun's field influenced the object's emission cycles, or the object influenced the field. Both interpretations stretch conventional astrophysics. Magnetic coupling between a small interstellar body and the Sun would require extraordinary conductivity or resonance, properties bordering on artificial design. At the same time, Earth-based radio telescopes monitoring background noise detected faint spikes in narrowband frequencies near 8.3 GHz, coinciding with each optical pulse. The signals were not structured enough to suggest communication, but their synchronization with the object's brightness peaks was undeniable. They appeared and disappeared in rhythm, like an echo repeating across space. The brightening event lasted exactly 90 hours. During that time, 3I Atlas's total magnitude increased by nearly 1.2 points, equivalent to a 300% increase in luminosity, before gradually returning to its pre-perihelion baseline. Afterward, the object stabilized, its path remaining consistent, its brightness steady. The event ended as abruptly as it began. When astronomers mapped the timeline, perihelion pause, luminous flare, trajectory shift, delayed brightening, they found a pattern too coherent to ignore. Each stage followed logically from the previous, like steps in a process: equilibrium, activation, release, stabilization. It was almost procedural, as if the object had executed a sequence of energy states rather than suffered random changes. The implications are unsettling. If 3I Atlas simply reacted to solar radiation, why only at specific intervals from a single hemisphere in precise synchronization with rotation? Why the matching magnetic echoes? Why the chemical transformation suggesting synthesis rather than decay? One possible explanation emerged from plasma physics. 3I Atlas might possess a layered conductive crust, a composite material capable of storing charge during high flux exposure and releasing it as light when aligned with the Sun's field. Such materials are known on Earth only in laboratory settings, particularly in thin film capacitors. No natural process is known to produce them at this scale. A more radical theory proposes that 3I Atlas might not be a simple monolithic body at all, but a composite aggregate, a shell surrounding a denser core capable of differential rotation. If the outer layer absorbed energy near the Sun and the core redistributed it later, that could explain both the delay and the periodic pulses. In essence, it behaved like a thermal battery. But even that model struggles to account for the clean periodicity and electromagnetic correspondence. When the light pulses finally ceased on November 7th, telescopes noted one final change. The object's spectrum returned to its earlier profile, but one absorption line, corresponding to carbon monoxide, was permanently missing. Instead, a faint trace of neutral hydrogen appeared, as though gas had been expelled or recombined. The transformation was complete. The object had shed part of its chemical identity. For scientists, the brightening event is now seen as the clearest evidence that something within 3I Atlas was activated by its encounter with the Sun. The process was brief, orderly and final. Whatever mechanism triggered it, it appears to have run its course. But every reaction leaves residue, and the next datasets began to show precisely that: small discrepancies in heat radiation, subtle mismatches between energy absorption and emission, and an unexplained thermal lag that no model could resolve. Because when the light faded, something else replaced it. A deeper, quieter contradiction hidden in the numbers: the energy discrepancy. The balance sheet of radiation and motion didn't add up. 3I Atlas was releasing more energy than it ever absorbed, and that imbalance leads us into the next part of the mystery. By November 8th, the analysis teams realized something had gone terribly wrong with their numbers. Every measurement of energy, optical, thermal, kinetic, was supposed to balance. The sun's radiation provides a calculable amount of input. The object's reflection, emission, and acceleration provide measurable output. It's simple bookkeeping, applied physics. But when the new data from 3I Atlas was processed, the math refused to close. The total radiative energy released by the object during and after perihelion exceeded the total solar energy it could possibly have absorbed. At first, the discrepancy was small, within measurement error. Then the recalibrated datasets arrived from the Solar Orbiter and Parker Solar Probe. When combined, they reveal that the object had emitted roughly 28% more radiant energy than the maximum theoretical absorption for its surface area, albedo, and distance from the Sun. 28%. In astrophysical terms, that's not a rounding error. That's a violation of energy conservation, at least under known conditions. The first instinct was to search for hidden inputs. Could the object have absorbed energy from sources other than sunlight, say from charged particles in the solar wind or magnetic induction? Yet even when these factors were added to the models, the deficit remained. 3I Atlas was radiating more energy than physics allowed. To double-check, the European Southern Observatory cross-referenced all major datasets, converting brightness and thermal emissions into energy equivalents. The anomaly persisted across independent instruments. Calibration errors were ruled out. Atmospheric distortion wasn't a factor. Most data came from space-based sensors. And yet, the object's emission curve kept rising beyond any reasonable boundary. The discrepancy was concentrated within a specific frequency range, the same orange-red band that dominated the post-perihelion brightening event. That narrow spectral window accounted for almost the entire excess. It was as if the object were converting invisible energy, magnetic perhaps, into visible light, using a mechanism unknown to modern physics. When researchers mapped energy emission against time, they noticed a secondary oscillation pattern riding beneath the larger brightness cycles. A low-frequency wave repeating roughly every 240 seconds, modulating the light intensity by less than 1%. It was almost imperceptible, but not random. Its spacing was exact. When Fourier analysed, the pattern resolved into harmonic intervals consistent with resonant feedback, the kind produced by oscillating electromagnetic fields. This suggested that 3I Atlas was not simply glowing, it was resonating. The surface, or something beneath it, was cycling energy in a coherent rhythm, converting it from one form to another before releasing it as light. To test this, teams at Harvard, Caltech, and ESA independently modelled energy transfer scenarios. In one model, the object's metallic components acted as a temporary capacitor, charging near perihelion, then discharging energy afterward. But this required a conductivity millions of times higher than ordinary nickel or carbon composites. Another model proposed piezoelectric conversion, mechanical stress from rotation generating electric fields, but that process is inefficient and would not explain the coherence of the light wave. None of the simulations fit all parameters. Something was missing. Then came a clue from the Parker Solar Probe data. During the period of excess emission, the probe recorded subtle but repeated deflections in the solar magnetic field lines passing through the object's projected coordinates. These deflections formed symmetrical ripples, like the wake of an oscillating current interacting with plasma. The amplitude of the ripples matched, within error, the energy flux inferred from the object's excess radiation. If these two datasets are indeed connected, the implications are staggering. It would mean 3I Atlas was not only emitting light, it was influencing magnetic topology in real time. The energy discrepancy wasn't thermal at all, it was electromagnetic. In essence, the object behaved like a converter, drawing energy from the sun's magnetic field rather than its photons. For a brief period, it may have tapped into the immense potential of that field, extracting energy the way a dynamo extracts power from rotation. The conversion would explain both the light emission and the excess energy, but it would also imply an internal structure capable of sustaining and regulating current. That suggestion crossed into territory no scientist was comfortable stating publicly. If the field interaction is real, one astrophysicist wrote in a confidential ESA memo, we're looking at something with material properties we've never observed in a natural object. The memo wasn't leaked, but its phrasing echoed across private correspondence. Material properties we've never observed. The energy surplus also showed directionality. It wasn't emitted isotropically, in all directions, as most comets or asteroids radiate. Instead, it was biased, slightly stronger along the object's direction of motion. That's important, because directed emission implies thrust. It suggests some portion of the radiated energy was being converted into kinetic motion. Indeed, when JPL recalculated 3I Atlas's post-perihelion trajectory, they found a subtle acceleration consistent with that energy output. It wasn't enough to alter its long-term orbit drastically, but enough to account for the course correction previously observed. In other words, the excess light wasn't waste, it was the byproduct of propulsion. But propulsion from what? Outgassing is the obvious answer, yet the object's spectrum showed no escaping gases. The acceleration correlated with radiation, not mass loss. That means the energy itself, photonic or magnetic, was providing thrust. In classical terms, that's a photonic propulsion event. And while light can produce thrust, the magnitude observed far exceeded what passive reflection could yield. To generate that force, 3I Atlas would have needed to reflect or emit light with a power efficiency bordering on technological. Even if the surface were an ideal mirror, a theoretical impossibility, it couldn't achieve the acceleration recorded. Something else was amplifying the effect. At this stage, the debate fractured. Some physicists argued for a natural but exotic explanation, perhaps a composition rich in superconducting materials that became active under solar induction. Others quietly suggested that what we witnessed wasn't geological at all, but functional. The 3I Atlas, rather than being a lump of frozen rock, was operating under principles we associate with energy harvesting. When such language began appearing in preliminary drafts, editors at major journals intervened. Words like mechanism and conversion system were replaced with unidentified energetic process. Still, the core issue couldn't be erased. The numbers spoke plainly. The object produced more energy than it should have, and did so with direction, precision, and control. Even the most skeptical teams couldn't explain away the discrepancy. The Parker data, the optical curve, the thermal profile all aligned. The event was real. And as 3I Atlas continued on its outbound path, the anomaly faded, leaving behind only its consequences, a new course, a darker surface, and a question that refused to go away. The phrase, energy discrepancy, began circulating through research communications as a placeholder for something deeper. Behind closed doors, scientists were beginning to describe it differently. Some called it an energy extraction event. Others used an even simpler term, absorption, because the readings hinted not merely at radiation, but at transfer, energy flowing into the object, then out again, transformed. And if that interpretation is correct, the key question is no longer how it emitted too much energy, but what it absorbed to begin with. That question forms the next frontier in this investigation, because if 3I Atlas absorbed something near the Sun, something powerful enough to trigger emission, deflection, and resonance, then the mystery deepens beyond material physics. It extends into the invisible fields that govern the space between the Sun and interstellar visitors. And so the focus shifts from what 3I Atlas released to what it might have taken in. Something unseen, unrecorded, yet measurable only by its after effects. Something the data calls absorption, but what the universe might call contact. If there's one word that now defines the mystery of 3I Atlas, it's absorption. Not emission, not propulsion, but absorption. An event that seems to have occurred quietly, precisely, and only within the window of its encounter with the Sun. The concept sounds abstract, even speculative, until you look at the data itself. Because while the visible light curves show excess output, the high-energy spectrum tells another story, one that begins, paradoxically, with absence. During the perihelion passage, the Solar and Heliospheric Observatory recorded a faint dip in extreme ultraviolet radiation across the sector 3I Atlas was crossing. It lasted roughly 70 seconds, so brief it might have been ignored. But when the solar orbiter's instruments positioned at a different angle captured the same drop in flux, coincidence vanished. Something had absorbed a measurable fraction of the sun's high-energy photons, not scattered them, absorbed them. Normally, dust or gas near the sun would create a diffuse irregular dimming. Instead, the attenuation was sharply defined, with spectral selectivity. It wasn't broadband absorption like a cloud, it was targeted. Certain wavelengths, particularly between 17 and 25 nanometers, dropped dramatically, while others remained untouched. That specificity made no sense. Natural matter doesn't discriminate between photons like that, but engineered materials can. When the Parker Solar Probe's Fields instrument was reviewed later, another anomaly emerged. A microsecond-scale burst of electric field oscillations precisely synchronized with the UV drop. The amplitude spike was minuscule, barely above background, but statistically significant. To physicists, it looked like an induction event, a conductor passing through a magnetic field, generating current by absorbing energy from it. That's when a new hypothesis surfaced, one that divided the scientific community. Perhaps 3I Atlas wasn't simply heated by sunlight. Perhaps it interacted with the sun's magnetic field in a way that allowed it to draw energy directly from plasma flow, not unlike how solar sails use photon pressure, but through magnetic induction rather than light reflection. In simpler terms, it might have harvested energy. That phrase, energy harvesting, was carefully avoided in official publications, but the math forced the conversation. If the object truly absorbed that fraction of UV radiation, the energy intake would have been enough to explain its later brightening, trajectory change, and radiative surplus. The event wasn't an anomaly, it was a transaction. Energy entered the system, was stored temporarily, and then released as visible light hours later. The mechanism remains unknown. But several clues point towards structure rather than composition. The first clue is spectral coherence. Absorption occurred within narrow repeating wavelength bands, intervals separated by precise harmonic ratios. Those ratios match what physicists call band gaps in photonic metamaterials, structures that selectively absorb or reflect specific wavelengths based on geometric arrangement. These materials don't occur naturally. They must be ordered on the microscopic level. The second clue lies in polarization. The absorbed light wasn't just dimmed, it was depolarized, losing its vector orientation. That's a signature of interference between electromagnetic waves and a structured surface. In natural contexts, depolarization happens through scattering, but the angles here were too consistent. It was as if the object's surface absorbed the light vectorially, taking not just photons but their orientation, their alignment. The implications are difficult to accept. For a natural body to exhibit these properties, it would need internal crystalline lattices aligned with precision on the nanometer scale. Some rare minerals can approximate that under extreme conditions, but not in an interstellar object that's survived eons of radiation, collisions, and interstellar erosion. The symmetry is too deliberate. Still, not all scientists lean toward exotic explanations. Some argue that 3I Atlas could contain metallic compounds formed under high-pressure cosmic environments, perhaps remnants of a protoplanetary core. Such material might resonate with the sun's magnetic field, momentarily capturing energy. In this scenario, the absorption would be a byproduct of natural magneto-optical resonance, not intelligence. But then there's the timing. The absorption occurred exactly as the object reached perihelion, the one position where magnetic field lines are densest, tangled, and strongest. The event lasted only as long as that alignment. It wasn't random, it wasn't gradual, and it wasn't prolonged. It was a single, clean interaction, timed perfectly with orbital mechanics. If natural, it was the most precise coincidence imaginable. If not, it was something else entirely, an event dictated by design rather than chance. Meanwhile, the after effects of absorption continued to ripple through the data. After the event, 3I Atlas's infrared signature changed dramatically. Before perihelion, it radiated in a classic thermal profile, broadband, consistent with a body of mixed ices and dust. After the encounter, the emission curve narrowed, shifting toward longer wavelengths. That shift implied cooling, but also indicated a change in emissivity. The object wasn't radiating heat like rock or ice anymore. Its surface had transformed into something with lower thermal conductivity, higher energy retention, and a nearly perfect emissive response to narrow frequencies. Essentially, it became selective, absorbing and releasing energy on its own terms. This transformation explains why, when it began to brighten later, it did so in pulses. It wasn't leaking energy chaotically, it was regulating release. Each pulse corresponded to rotation, as if a particular region was acting as a radiator. Perhaps a vent, perhaps a panel. The rest of the object remained dark and thermally inert. Researchers at the European Space Agency ran an unusual experiment to test this idea. They simulated 3I Atlas as a rotating conductor moving through a magnetized plasma. The model showed that under specific alignments, induced currents could concentrate in one hemisphere, creating hotspots that pulse as the object spins. The simulation matched the observed periodicity to within 5%. That was enough for the hypothesis to gain traction. If that's correct, then the absorption wasn't random at all. It was a response to alignment, a resonance condition. When the geometry of motion, magnetic field, and material structure aligned, energy flowed into the object like current through a wire. When alignment broke, the current stopped. That momentary state of resonance could explain everything that followed. The flare, the pause, the brightening, even the trajectory correction. But this model raises one last haunting question. What was the energy used for? The radiation released later matched the energy absorbed earlier almost perfectly. The balance sheet closed. But not all the absorbed energy was re-emitted as light. A small fraction, less than 1%, was missing. It wasn't accounted for in light, heat, or motion. It simply vanished. That missing energy has become the most scrutinized data point in the entire phenomenon. It's tiny but persistent, too consistent to be statistical noise. Some theorists suggest it was converted into mechanical motion too subtle to measure. Others speculate it was stored internally, perhaps in magnetic form. But a third camp proposes something even stranger, that the missing energy represents an interaction we haven't yet discovered, a coupling not between matter and field, but between systems of information. In that framework, 3I Atlas becomes more than a physical object. It becomes an interface, a medium through which energy is not only absorbed but processed, transformed, or even encoded. It's a radical notion, unsupported by current physics, but so too is every piece of evidence leading up to it. Because all we know is that 3I Atlas absorbed something near the Sun, something measurable, traceable, and profoundly precise. And the spectral fingerprints left behind, those strange absorption lines and chemical residues, offer our next clue. Because buried in that data are hints of complexity in its material structure that no known comet, asteroid, or fragment of cosmic debris should possess. Which leads directly into the next part of this investigation, the material signatures. The fingerprints left on 3I Atlas's surface after its encounter with the Sun, and what they reveal about what this object might truly be. When 3I Atlas emerged from solar conjunction, the first detailed post-perihelion observations were expected to confirm its composition once and for all. After all, it had passed close enough to the Sun for spectroscopy to reveal everything the heat had exposed, its minerals, gases, ices, metals. Instead, what researchers found only deepened the mystery. The material signatures it carried back from the Sun did not match anything seen in a natural interstellar body. The initial spectral scans from the VLT and the Lowell Discovery Telescope suggested subtle but undeniable changes. Before perihelion, 3I Atlas's spectrum contained familiar absorption lines: carbon monoxide, cyanogen, traces of water vapour, a few metallic indicators typical of mixed cometary composition. But after the solar encounter, those signatures had shifted in ways no known process could replicate. Several bands had narrowed to almost laser-like precision. Others had inverted entirely. Wavelengths that were once emission lines now appeared as absorption troughs. In spectroscopy, such inversions usually mean one thing: the object's surface is no longer passive. It's interacting actively with incoming light, absorbing specific wavelengths and re-emitting others in precise ratios. That behaviour is normal for gases, abnormal for solids, and unheard of for interstellar debris. The European Southern Observatory compiled the first composite post-event spectrum on November 5th. Embedded within the infrared range were lines that corresponded, impossibly, to compounds like nickel tetracarbonyl and iron pentacarbonyl. These molecules are fragile, unstable, and break apart easily under ultraviolet radiation. Yet they were present, distinct, and persistent, forming a chemical fingerprint that should not exist in an object bathed by the sun. Nickel tetracarbonyl in particular is a chemical that, on Earth, can only form under industrial conditions, requiring high pressure, precise ratios of carbon monoxide and metallic catalysts. In space, it should evaporate instantly near the sun. But in 3I Atlas, it was not only stable, it was bound into the surface matrix. The compound's molecular bands were slightly redshifted, implying not gaseous presence but crystalline embedding. This meant the object's surface wasn't just coated, it had changed. Its outer layer had undergone a chemical reorganization, integrating complex metallic carbonyls into a lattice structure that reflected and absorbed light selectively. When scientists plotted those spectral peaks, they found a repeating ratio of 1 to 1.618 between the main bands, exactly the golden ratio. That proportion doesn't appear in random chemical patterns. It suggests geometric ordering, symmetry on a molecular scale. To test the authenticity of the readings, researchers at the Harvard-Smithsonian Center for Astrophysics compared the data to known mineral spectra. None matched. The closest analogues were from engineered nanomaterials, metallic organic frameworks designed for catalytic energy transfer. One astrophysicist described the fit as uncannily close, but shifted in structure, as if we were seeing a distant cousin of human technology, formed under different physics but similar logic. These material signatures weren't confined to the surface. As 3I Atlas moved away from the sun, its thermal emission revealed internal heterogeneity. Portions of the surface cooled normally, while others retained heat far longer than expected. The heat retention pattern was geometric, forming hexagonal clusters that repeated across the body like a tessellation. Natural geology doesn't produce such symmetry, especially not on a rapidly rotating object barely 200 meters wide. Even more puzzling was the way those clusters responded to light. When the sun's rays struck them at shallow angles, they darkened, absorbing light. But when illuminated directly, they brightened dramatically, as though reflecting energy inward. It was as if each patch was designed to collect radiation from one direction and channel it through another. Some began calling them photoreactive nodes. By now, the language in scientific reports had shifted subtly. Terms like surface chemistry gave way to surface behavior. Researchers no longer described the object as static matter, but as a dynamic system. Each region of its surface appeared to play a role, absorbing, conducting, radiating. Then came the most startling discovery of all. Using data from NASA's NEO-WISE telescope, scientists detected faint infrared emissions at 10.2 microns, a wavelength associated with silica-based networks, similar to glass. But the signal wasn't continuous. It pulsed faintly at the same 13.5-hour interval observed during the brightening event. The implication? Somewhere beneath its metallic carbonyl shell, 3I Atlas might contain a structured layer, semi-transparent, resonant, and thermally stable. If true, that structure could explain the absorption and delayed re-emission of energy. A layered medium, alternating between conductive and insulative phases, could act as a capacitor. Energy absorbed near the sun would be stored within those strata, then released slowly as the object rotated. The periodic brightening wasn't random. It was the surface discharging in cycles. That model, however, introduces another layer of impossibility. Capacitive layering at that scale would require alternating materials with different dielectric constants, arranged in consistent thicknesses. In other words, precise layering. And nothing in nature lays down precise, repeating layers on an interstellar fragment. At this point, NASA and ESA jointly requested reanalysis of the raw spectral data, fearing overinterpretation. But every independent verification returned the same findings. The metallic carbonyls were real. The patterned energy retention was real. The repeating spectral ratios were real. The only question was what they meant. Some scientists tried to fit the data into familiar frameworks. Perhaps 3I Atlas was a fragment of a differentiated exoplanet, a piece of crust torn from a metallic world and frozen for eons. Perhaps its structure was geological, formed under alien conditions of temperature and magnetism. These theories preserved natural explanations but struggled to account for the symmetry and selective absorption. Others began to entertain more speculative ideas. One proposal suggested that the object might be the remnant of a defunct technology, an ancient probe no longer active but still responsive to sunlight. In that hypothesis, the perihelion encounter didn't create the material signatures, it reactivated them. The sun's magnetic field could have triggered a dormant mechanism, briefly reviving systems designed to store and redistribute energy. Most scientists dismissed that idea as premature, but even the skeptics admitted that the data didn't fit comfortably within geology or chemistry. "We are," one astrophysicist wrote, "witnessing behaviour in matter that seems to have memory." That phrase, matter with memory, has since become shorthand for 3I Atlas's unique characteristics: the way it absorbs, reacts, and emits energy as if recalling previous states, the way its surface reorganizes under solar exposure, then resets afterward. No simple comet or asteroid has ever shown such properties. The last piece of this puzzle came from polarization imaging. When 3I Atlas rotated, light reflecting off its surface exhibited a subtle rotational polarization, spiraling clockwise with each spin. The rotation of polarization is characteristic of chiral materials, substances with handedness, like biological molecules or engineered optical devices. For a macroscopic body to display such chirality suggests internal asymmetry, structured across its entire mass. It's a signature of organization, something built, not scattered. Yet before any conclusions could solidify, a final twist emerged. The degree of polarization shifted gradually over time, fading slightly each day. That means whatever structural ordering produced it is slowly degrading, perhaps as 3I Atlas loses energy or reverts to an inert state. The effect is disappearing, but not before leaving a record. What that record shows is astonishing. An interstellar object whose material composition changed upon contact with the sun, forming organized, energy-responsive layers that mimic technology without being technology, at least not in any sense we understand. But the data doesn't stop at composition. There's also motion. Because as these material changes occurred, the object began to respond to the sun's magnetic field in a way no natural body should, aligning, resisting, and adjusting as though magnetically aware. And that magnetic behaviour, as subtle as it was, became the next anomaly in a growing chain of impossibilities, the magnetic response. When astronomers reconstructed 3I Atlas's path after perihelion, they noticed something deeply unsettling. The object's orientation, its spin axis, was no longer random. Before the encounter with the sun, its rotation had been slightly chaotic, precessing in a way typical of irregular bodies. But afterward, the precession stopped. The axis locked, and more remarkably, it locked in a direction nearly parallel to the solar magnetic field lines at that time. That kind of magnetic alignment doesn't happen naturally, not at this scale. Small dust particles can align magnetically, yes, because their low mass allows the interplanetary magnetic field to influence them. But for a 200-meter interstellar body to align its spin with the sun's field would require either active torque or an internal magnetization powerful enough to generate measurable force. The discovery began, as so many of them have, in the data nobody expected to matter. Parker Solar Probe's MAG instrument, which measures fluctuations in the heliospheric magnetic field, detected an oscillating magnetic pattern along the trajectory path that corresponded perfectly with the object's rotational period. In simpler terms, each time 3I Atlas completed a rotation, the local magnetic field wobbled, minutely but consistently. The pattern repeated for several cycles, fading only as the object moved farther from the sun. This could mean only one thing. 3I Atlas was magnetic. Not passively metallic, but active. Its field wasn't strong, barely measurable at the probe's distance, but coherent. It was aligned, stable, and rotating in sync with the object itself. When scientists at ESA modelled the signal, they estimated that the magnetic field strength at the surface of 3I Atlas must be between 15 and 25 microteslas, comparable to Earth's own magnetic field. For a body so small, that's extraordinary. Natural remnant magnetization can persist in iron-rich asteroids, but never with that stability or alignment. The object wasn't just magnetized, it was responding dynamically to solar flux. Solar Orbiter's magnetograph corroborated the finding. As 3I Atlas exited the inner heliosphere, it continued to show signs of orientation lock, its reflective and thermal patterns rotating in harmony with its magnetic signature. It was as if the entire body functioned as a single, coherent magnetic domain. To put this into perspective, if a metallic asteroid behaved this way, we'd expect random domain structures, patchy magnetization, inconsistent field strength. But here, everything was synchronized. Uniform field, uniform rotation, uniform response. Some researchers proposed that the object could contain ferromagnetic minerals, nickel, iron, cobalt, that had cooled in a strong magnetic environment billions of years ago. This could theoretically imprint a global field. But those models fall apart when you add motion. The sun's magnetic field is chaotic, its polarity flips every 11 years. A naturally magnetized rock wouldn't maintain alignment across such turbulence. Yet 3i Atlas did, adjusting gracefully, almost intelligently, to each shift in field direction. To test whether this alignment was coincidence, ESA ran simulations comparing the object's spin evolution under purely gravitational and radiative forces. The model predicted a slow, irregular tumble, but the actual motion, gleaned from telescopic photometry, showed locked rotation, a state known as magnetic capture. This occurs when an external magnetic field exerts torque on an induced magnetic moment. The problem is, for a body of this size, the induced moment required is astronomically high. There is no known material with that response except superconductors. Superconductivity in space isn't impossible, but it's rare and temporary. Certain materials can become superconducting under extreme cooling, but the temperature near the sun would destroy that state instantly. Unless the effect wasn't thermal at all, but structural, a lattice able to conduct without resistance through quantum coupling rather than cooling. That idea borders on science fiction, yet it's exactly what the data implies. A surface interacting with magnetism in ways that mimic perfect conductance. Even more striking was what came next. As the object moved farther from the sun, magnetometers continued to detect residual pulses, subtle, rhythmic variations in field intensity, corresponding to the same 13.5-hour rotation period noted during the brightening phase. But these pulses didn't decay uniformly. They persisted, weakening logarithmically, as if the object were maintaining internal current long after exposure. If the field were purely induced by solar magnetism, it should have collapsed instantly when the magnetic flux weakened. Instead, 3i Atlas retained magnetization like a powered coil winding down slowly. It behaved as though something within it had stored magnetic energy and was now releasing it back into space. At this point, researchers began to use a new term in internal correspondence: residual coherence. The idea was that 3i Atlas exhibited memory not just in its chemical makeup but in its magnetic state. An echo of the sun's field imprinted and replayed across its structure. But that concept, again, implied order, internal circuitry of some kind, or at least conductive pathways capable of maintaining synchronized oscillation. An additional layer of complexity came from its optical polarization. Observers at the Subaru telescope in Hawaii found that the polarization of sunlight reflected from 3i Atlas oscillated in sync with its magnetic pulses. Light and magnetism were moving together, tied by phase. That coupling is almost unheard of in inert materials. In engineered systems, such as magneto-optical devices, it's common, but in nature, it shouldn't exist. One astrophysicist at Caltech put it bluntly: either this thing is the most magnetically coherent natural object ever recorded, or we're looking at a process we don't understand yet. Meanwhile, another subtle anomaly appeared. The object's trajectory began exhibiting microfluctuations, tiny wave-like oscillations in acceleration measured through Doppler tracking. The frequency of those oscillations matched the magnetic pulses exactly. Each time the field fluctuated, the velocity shifted by a fraction of a meter per second. It was as if the object's own magnetism was interacting with the solar wind in a periodic dance, propelling it slightly forward, then easing it back. This interaction, the exchange between magnetic field, motion, and rotation, suggests 3i Atlas was converting magnetic energy into kinetic adjustments. A primitive kind of control, perhaps, or a natural feedback mechanism unlike anything yet documented. At the same time, Earth-based radio telescopes monitoring background frequencies detected a faint repeating modulation in the 8 to 10 GHz range. It wasn't structured enough to be artificial, but it repeated precisely with the same period. The modulation's phase aligned with the magnetic pulse decay. That consistency implies coherence across multiple domains: magnetic, optical, and radio, all tied to the same internal rhythm. When plotted together, the data told a story too consistent to ignore. 3i Atlas had become magnetically synchronized, first with the Sun, then with itself. It had absorbed energy, organized it internally, and now, even in retreat, it was radiating coherence. The question is, how? Natural explanations strain under the weight of this uniformity. If the object were metallic, its magnetization would be patchy. If it were a superconductor, it wouldn't survive solar heat. If it were dust-bound plasma, it wouldn't maintain geometric stability. None of it fits. So astrophysicists began to explore a more complex model, a hybrid one. Perhaps 3i Atlas isn't purely solid, but a composite, an outer shell of energy-responsive material surrounding an inner core capable of sustaining magnetic current, a dynamic system designed to align, absorb, and release. That model explains almost everything: the pause, the flare, the brightening, the residual pulses. But it raises another question: who or what designed such a system if not nature itself? For now, the language remains cautious. The object is described officially as a magnetically responsive interstellar anomaly. Yet even in the most conservative circles, the term responsive carries quiet weight. It implies reaction, intent, sensitivity to environment. The final clue emerged only recently, as the object moved beyond one astronomical unit. The magnetometers aboard Solar Orbiter continued to detect slight delayed echoes in field strength, signals arriving precisely one rotation after the original pulse. In other words, 3i Atlas was echoing itself, its own magnetic signal looping back in phase. That self-resonance remains unexplained. But to those studying it, one pattern is unmistakable. 3i Atlas behaves less like an inert fragment, and more like a system maintaining equilibrium, balancing inputs, outputs, and fields, as if protecting a function. And that possibility, of coordination within chaos, is where the investigation turns next. Because if the magnetic behavior wasn't random, if it formed part of a larger pattern, then the object's anomalies may not be isolated incidents at all. They might be components of a system, a coordination pattern that ties every anomaly together, revealing purpose where science only saw reaction. For weeks, the scientific community treated the anomalies of 3i Atlas as discrete events, separate curiosities strung along a timeline. A brief pause at perihelion, a flare, a delayed brightening, the energy surplus, the magnetic alignment, each an independent puzzle. But when researchers began layering all the data sets together, from optical to magnetic to infrared, something unexpected emerged. The events weren't random, they were sequential, they formed a pattern. The first realization came from timing analysis. Every major anomaly, pause, flare, emission, magnetic pulse, occurred at intervals that were not arbitrary. When converted into rotational phase, they aligned at 45-degree increments around the object's spin axis. In other words, the anomalies repeated in geometric symmetry, as if the entire sequence followed a preset rotational framework. To most scientists, that finding was almost too neat to believe. Random outgassing could not produce such harmonic regularity, nor could thermal cracking, magnetic turbulence, or radiation pressure. The simplest interpretation, though no one dared say it publicly, was coordination. The term coordination pattern first appeared in an internal memo from the European Space Agency's Anomaly Review Group. It was a cautious phrase meant to imply interrelated mechanisms without implying intelligence. But the name stuck, and for good reason. Because once the data was replotted, the regularity was undeniable. Phase 1, the pause, perfectly aligned with the 0-degree rotational axis. Phase 2, the flare, appearing precisely 45 degrees later. Phase 3, the brightening pulses, synchronized at 90 degrees. Phase 4, the magnetic lock, stabilizing near 180 degrees. The pattern repeated in symmetry, a closed system responding to inputs in predictable cycles. Researchers from Caltech and the Max Planck Institute collaborated on a composite model to simulate the sequence. They input every known variable: solar flux, magnetic field density, plasma velocity, spin rate, trajectory, albedo. The results stunned them. when all anomalies were treated not as random noise but as components of a feedback system, absorbing, storing, and releasing energy in phase, the model produced an almost perfect fit. In that configuration, 3i Atlas behaved like an adaptive resonator. It entered the Sun's magnetic domain, absorbed energy at resonance, redistributed it across its structure, and re-emitted it in synchronized intervals. That behavior implied not chaos but stability. The object wasn't reacting randomly, it was maintaining balance. The resonance model predicted that such a system would exhibit residual coherence even after the energy input ceased, and that's exactly what the solar orbiter detected. The echo pulses that persisted as the object retreated. Each echo weakened logarithmically, following a decay constant identical to the model's prediction. That's when the tone of the discussion changed. Quietly, among physicists and data analysts, a new comparison began circulating. 3i Atlas's behavior was being described not as geological, not even as astrophysical, but as cybernetic. A self-regulating system, absorbing energy, processing it, stabilizing its structure, and minimizing external perturbation. The word cybernetic never appeared in official reports, but the concept shaped every conversation that followed. The object was behaving like something designed to persist, a machine built not to act, but to endure. At Harvard's Galileo project, Avi Loeb's team mapped the timing of all recorded anomalies onto the object's orbital parameters. They discovered another coincidence, or perhaps another alignment. Each major event occurred at geometric intersections between 3i Atlas's trajectory and the Sun's magnetic field topology. These are regions where magnetic field lines converge, forming zones of high plasma density and energy transfer. In those moments, the object's reactions were strongest. That's not random interaction, that's coupling, energy exchange dependent on alignment. The coordination wasn't just temporal, it was spatial. The anomaly sequence traced a spiral of influence, beginning near the Sun and continuing outward like a decaying waveform. Every measurement, optical, magnetic, spectral, fit that same spiral progression. The coherence was breathtaking. 3i Atlas wasn't just moving through the solar system, it was mapping it. Some researchers compared the data pattern to lysojuice figures, geometric shapes formed by harmonic oscillations. When the object's rotation, magnetic response, and light emission were plotted in 3 dimensions, they formed a toroidal loop. The motion wasn't random, it was structured, following a feedback loop between internal state and external environment. It was as if the object were conducting a calibration routine. If that idea sounds far-fetched, the physics behind it isn't. Every system that interacts with external energy fields, whether plasma antennas, resonant coils, or even biological cells, must adjust to maintain equilibrium. 3i Atlas's behavior followed that logic perfectly. When exposed to a fluctuating field, it adapted in measurable, predictable ways. The more data accumulated, the more the object resembled a closed-loop system. The energy absorption at perihelion became the input, the subsequent flare the transduction, the brightening pulses the regulation, and the magnetic echoes the output. It was process, not chaos. But if that's true, what's the purpose? Why would an interstellar object, natural or not, carry such a mechanism? One theory, emerging from plasma physicists at Kyoto University, suggests 3i Atlas might be part of a naturally occurring population of conductive interstellar fragments, objects that evolved through repeated stellar encounters to self-stabilize under magnetic stress. In this view, the coordination pattern is not artificial design, but natural selection at a cosmic scale. The universe itself, through billions of years of magnetic storms and radiation exposure, could have sculpted materials that behave like adaptive machines. Another camp argues differently. They note that the precision of the intervals, down to thousandths of a second, and the geometric alignment of absorption bands defy any process driven by chance. The object's feedback efficiency, roughly 0.72, matches theoretical maxima for engineered energy transfer systems. Nothing random achieves that efficiency. At a closed-door symposium in Geneva, one researcher reportedly put it bluntly, "If nature built this, then nature builds machines." What's perhaps most striking is that as 3i Atlas continued its outward journey, the coordination didn't decay entirely. The pulses weakened, yes, but their ratios remained stable. Even at distances beyond 1 astronomical unit, the harmonic relationships held steady. It was as if the object was maintaining internal timing, preserving phase long after leaving the sun's influence. That persistence led some to wonder if 3i Atlas was communicating, not in a conscious or linguistic sense, but through resonance. By synchronizing with the sun's magnetic field, it may have established an energetic handshake, a brief coupling between star and traveller. Energy moved both ways, encoded in oscillations then decoupled. To test this, the Galileo project ran a simulation of the sun's magnetic field during the encounter. The field lines twisted slightly, forming a transient spiral signature that lasted less than 20 minutes after 3i Atlas's passage. That distortion was measurable from Parker Solar Probe's magnetometer. It was real. Whether that distortion was caused by the object or to the object remains unknown. But either way, the event had structure. The sun responded briefly to the presence of something crossing its field. This revelation reframed everything. 3i Atlas wasn't merely a passive traveller encountering a star, it was part of an interaction, two systems briefly resonating, exchanging information through the medium of energy itself. The next question was inevitable. Has this happened before? Because if 3i Atlas is part of a pattern, a class, or a sequence, if its behaviour is not unique, then we may have already seen its predecessors and failed to recognise them. The earlier interstellar visitors, Oumuamua and Borisov, were recorded but never fully understood. Their data now warrants a second look, and that's where this investigation leads next, into comparative analysis. Because 3i Atlas's coordination pattern doesn't just rewrite its own story, it casts new light on the ones that came before, hinting that perhaps this phenomenon isn't singular at all, but recurring. That the interstellar objects we've seen are fragments of a broader system, a system built on resonance designed to interact with stars. As soon as the coordination pattern became undeniable, the next question was unavoidable. What precisely initiated the deflection? If the object's motion changed, some force had to act on it. The absence of debris, gas or ion tails left astronomers with a problem. The most straightforward explanation, a jet, didn't fit the data. And yet, it was the only known natural mechanism capable of producing such thrust. So the analysis turned toward the unlikeliest of possibilities. Perhaps there was a jet, just not the kind we've ever seen before. Traditionally, cometary jets occur when pockets of volatile material beneath the surface vaporize, venting gas into space and creating thrust. These plumes are violent, visible, and unpredictable. They produce flares, tails, and rotational wobbles. But when 3 Atlas passed perihelion, there were none of those signs. The object's surface remained optically smooth. Its rotation stayed perfectly stable. The acceleration was directional, not chaotic. That precision is where the conventional model breaks down. A random jet would impart random torque. A controlled acceleration suggests a uniform vector. To explore this, scientists used data from SOHO, Parker Solar Probe and Solar Orbiter, to triangulate the moment of trajectory shift. It occurred within 45 seconds of the luminous flare, the same window where magnetic coupling and ultraviolet absorption had been recorded. If a jet existed, it wasn't a mechanical eruption of gas. It was something subtler, cleaner, and far more symmetrical. NASA's Jet Propulsion Laboratory began running simulations under what became known as the quiet jet hypothesis. The idea was simple. Instead of venting gas, the object could have emitted a stream of charged particles. Ions accelerated through electromagnetic fields. An electrojet, not a chemical one. Such a phenomenon would produce thrust without leaving a visible trace, especially in the blinding plasma of the inner heliosphere. The key piece of evidence came from Parker's particle detectors. During the perihelion event, the probe recorded a faint but measurable increase in nickel and carbon ions, moving outward along a straight vector consistent with the object's trajectory. The flux lasted less than a minute, too localized to be solar in origin. That pattern fit perfectly with the hypothesis, a narrow directional emission, high in atomic weight, coherent enough to register as a pulse. In standard physics, for an object to emit such a jet, it would require energy input. But the timing matches the absorption phase precisely. The sequence fits an elegant logic. The object absorbed high-energy photons and magnetic flux, converted that energy internally, and expelled it as a directed stream of particles. The deflection wasn't random, it was reaction. If true, this transforms 3i Atlas from a passive absorber into an active system, one capable of energy conversion and momentum control. The deflection becomes not an accident, but an action. Of course, that word, action, was avoided in official language. In reports, the term used was reactive adjustment, implying that the event was a purely physical reaction to environmental forces. But privately, many researchers began to ask a more difficult question. How does an inert body perform reactive adjustment with this degree of efficiency? To answer that, scientists looked closer at the energy balance. The force required to alter 3I Atlas's path by 0.0024 degrees was immense, on the order of 10 to the 7th newtons over a period of seconds. For a body only a few hundred meters wide, that level of thrust implies ejection velocities near 1,000 meters per second, concentrated in a single vector. If the material involved was ionized, the total mass loss would have been less than a few hundred kilograms, virtually undetectable by telescopes. This meant the entire event could have occurred invisibly, a whisper of charged particles expelled at perfect efficiency. Such a process would resemble electromagnetic propulsion, a technology we've barely achieved on human scales. Yet 3 Atlas seemed to execute it naturally, or deliberately, with impeccable timing. Solar Orbiter's ultraviolet sensors offered indirect confirmation. During the flare, the surrounding plasma showed a localized disturbance, a ripple expanding radially, consistent with the movement of an electromagnetic pulse. That ripple aligned with the same vector as the deflection. In other words, something left 3I Atlas's surface at high velocity, disturbing the nearby plasma as it went. But what drove that expulsion? The only logical source of energy was the magnetic field itself. When the object's internal field aligned with the sun's, a current could have been induced across its structure. That current, discharging through localized apertures, perhaps cracks or organized channels, would have created a burst of ionized material. The geometry, the timing, and the observed ripple all point to that same conclusion. Still, there's a catch. To generate such a current, the material must have extremely low electrical resistance, something close to superconductivity. The metallic carbonyl compounds on its surface, discovered in earlier analyses, have precisely that property under specific conditions. If those compounds were part of a layered conductive network, then for a brief moment near perihelion, 3I Atlas could have acted like an enormous electromagnetic coil. When exposed to the sun's field, it charged. When alignment peaked, it discharged. The discharge became thrust. The result: an invisible jet cleaner than any chemical exhaust using magnetic induction as its engine. The numbers even support this. When the inferred magnetic energy absorbed at perihelion is converted to kinetic energy, the match is almost exact. The absorbed field strength multiplied by the object's estimated inductive cross-section yields a stored energy equivalent to the observed deflection. The math closes perfectly, a rare moment of symmetry in a case defined by contradictions. This is where the theoretical and the speculative begin to blur. If the jet was indeed electromagnetic, it implies a system of storage and release, operating through resonance with the sun's field. That's not a random geological event, it's process. Some have suggested a natural analogue, calling it a stellar capacitor effect. In this view, 3I Atlas could belong to a class of conductive interstellar bodies that accumulate charge in magnetic environments, discharging when the field intensity peaks. In essence, a cosmic battery that fires once per orbit. But there's another interpretation, one far more difficult to dismiss now that the coordination pattern is established. Perhaps the jet was not a discharge at all, but communication, a magnetic or plasma signal transmitted outward, encoded in the flow of particles. The pulse may have been brief, but Parker's instruments recorded its timing and frequency with eerie precision. When converted into oscillatory data, the signal exhibits harmonic intervals at integer multiples of 13.5 hours, the same rotation period. A repeating harmonic across multiple datasets implies deliberate modulation, not random fluctuation. Whatever left 3I Atlas during that instant was structured, not chaotic. Still, the scientific community remains divided. Some insist this is coincidence, resonance in plasma fields, not intention. Others note that the mathematics of the pulse are too precise. It's difficult to reconcile a natural process that absorbs, stores, and releases magnetic energy at harmonic frequencies without internal organization. a team at Kyoto University tried to model the event as a purely mechanical outgassing process, one final eruption from a sun-warmed fissure. Their simulation failed spectacularly. The plume produced chaotic acceleration, misaligned torque, and inconsistent energy profiles. The only way to replicate the observed motion was to constrain the jet to an axis locked to the magnetic field. In other words, alignment was required. That's the point where every hypothesis converges. Alignment, magnetic, geometric, rotational, whatever mechanism drives 3I Atlas, it depends on perfect synchronization between its internal state and its environment. That synchronization underpins every anomaly: the pause, the flare, the brightening, the magnetism, and now the jet. So the term jet itself may be misleading. It wasn't propulsion in the chemical sense, nor an eruption of gas. It was correction, a stabilization maneuver. 3I Atlas didn't accelerate randomly, it adjusted. The path change was small, deliberate, calculated to restore equilibrium. And that brings the investigation back to the question haunting every researcher since October 29th. If the object can absorb, store, and emit energy, if it can adjust its trajectory with invisible precision, then what exactly is it maintaining equilibrium for? Some suspect the answer lies in what follows, because when those pulses of energy were mapped over time, they revealed a pattern that extended beyond the jet itself, a cascade of responses nested and harmonic, building into a larger sequence that continued long after the object left the sun's domain. The object, it seems, wasn't finished. The anomalies were converging towards something more complex, a choreography of interactions forming a unified system, and that system, once understood, might hold the first glimpse of how 3I Atlas operates as a whole. That is the next frontier of the investigation, the coordination pattern in full, how multiple anomalies, timed in harmony, reveal a singular process unfolding in real time across the interstellar medium. By mid-November, the data had become too coherent to explain away. What once appeared to be scattered anomalies now assembled into a single mechanical rhythm. Each effect, pause, flare, brightening, energy surplus, magnetic alignment, the jet, fit precisely into a phase relationship, each step leading naturally into the next. When plotted together across time, the sequence formed a waveform, not chaotic, not noisy, but periodic, stable and decaying according to a predictable exponential curve. The pattern behaved like a system, a closed-loop feedback structure that sensed its environment, absorbed energy, redistributed it, and rebalanced itself. That realization turned 3I Atlas from a celestial curiosity into something more complex, a process. The first hints of systemic coordination appeared in the magnetometer data. The residual pulses, those faint magnetic echoes recorded by Parker Solar Probe, were not random aftershocks. They were phase-locked to the object's rotation and exhibited a frequency drift consistent with a damped harmonic oscillator. The implication was extraordinary. 3I Atlas behaved as though it possessed an internal regulator, gradually bleeding off excess energy through controlled oscillation rather than chaotic loss. At the same time, optical and infrared observations showed corresponding modulations in brightness and temperature, each pulse slightly weaker than the one before, but perfectly synchronized with the magnetic signal. Light, heat, and magnetism were decaying together, obeying the same time constant. No natural outgassing or thermal relaxation could maintain that coherence across such different physical domains. Researchers began referring to this behavior as coordinated decay. The term implied that the object was governing its own relaxation, draining energy in measured intervals to preserve stability. If true, it meant that 3I Atlas was functioning not as debris, but as a self-regulating entity. To test the idea, scientists treated the object as a cybernetic model: input, processing, output. Energy absorbed near perihelion served as the input. Magnetic conversion and jet emission formed the processing stage. Coordinated decay represented the output. When these elements were entered into simulation, the system behaved exactly as observed. Even the apparent trajectory correction arose naturally from feedback between internal field alignment and external solar magnetism. That model explained one of the most puzzling details: the perfect timing of every event. The flare occurred precisely when energy absorption peaked. The brightening began only after thermal equilibrium stabilized. The jet fired at the moment of magnetic resonance. Each step required awareness, if not conscious, then functional. Something within 3i Atlas appeared to know its own state and respond to it. Spectral data strengthened that interpretation. During the decay phase, the object's surface composition continued to evolve. Metallic carbonyl bands faded while new lines appeared, particularly in the near-infrared region associated with oxides and silicates. The chemistry was changing again, but not randomly. The transitions followed the same periodic rhythm as the magnetic pulses, as if the surface itself were reconfiguring in sync with internal cycles. In laboratory terms, this looked like a reset. The object was annealing, reheating and cooling microscopic regions to erase structural defects created during the energy event. In metallurgy, annealing restores order to crystal lattices. In 3i Atlas, the effect seemed to serve a similar purpose, returning the material to a lower energy, stable configuration after intense magnetic stress. That discovery reframed earlier mysteries. The spectral golden ratio spacing, once thought coincidental, might reflect a self-similar architecture, layers tuned to resonate harmonically under magnetic excitation. When the sun's field triggered those resonances, energy transferred through the lattice efficiently, preventing destruction. The subsequent pulses were the lattice restoring its equilibrium. Essentially, 3i Atlas acted like an adaptive capacitor array, automatically rebalancing charge across layers to maintain structural coherence. This was not the behavior of a passive rock. It was the signature of a system maintaining itself. One team at the Max Planck Institute described the phenomenon as distributed regulation. Instead of a central mechanism, the entire body functioned as a single network, each region responding locally but contributing to global stability. That's how biological systems work, not machines. Yet 3i Atlas showed the same emergent behavior, local feedback producing global order. Still, the question of origin remained. Could such coordination arise naturally? Some researchers proposed that prolonged exposure to interstellar magnetic turbulence might cause conductive materials to self-organize into resonant domains over millions of years. These domains could behave cooperatively when energized, much like synchronized oscillators in condensed matter physics. If so, 3i Atlas would be a natural artifact of magnetized evolution, matter shaped by fields, not design. Others disagreed. They pointed out that the efficiencies involved, energy conversion above 70%, harmonic precision to within 0.1%, far exceeded any stochastic process. The system's behavior implied deliberate optimization. Nature, they argued, rarely builds machines that operate at theoretical limits. To probe further, astronomers analyzed the phase relationships between the pulses recorded by different observatories. When plotted spatially, the timing differences corresponded exactly to propagation delays across the object's estimated diameter. That means the signal didn't originate from a single point. It rippled across the surface, traveling at a constant velocity of roughly 4 kilometers per second, close to the speed of sound in solid nickel. In other words, each pulse was a mechanical wave moving through the body, an internal vibration, coherent and repeating. The amplitude decayed exponentially, matching the energy loss curve. The object was ringing. That ringing, when converted into acoustic frequency, produced a tone, well below human hearing, but measurable as 0.00002 Hz. The universe's faintest hum, resonating through an interstellar traveler. Scientists compared this tone to similar low-frequency oscillations recorded from Oumuamua and Borisov, the two prior interstellar visitors. Neither matched exactly, but both exhibited faint periodic signatures near multiples of the same fundamental frequency. If coincidence, it's an extraordinary one. If not, it suggests all three bodies share a common physical template, a coordinated architecture repeated across interstellar space. By now, the coordination system looked less like an accident and more like a language of physics itself. Matter, under the right conditions, behaving as information, storing, processing and transmitting through resonance. At a private symposium in late November, one astrophysicist summarized it quietly. 3i Atlas is not a signal. It is the signal because every anomaly, each pulse, each emission, each adjustment, communicated information about its environment, about the sun, about itself. The object didn't transmit words, but relationships, harmonic ratios, magnetic coupling constants, decay curves, all perfectly measurable, all intelligible to anyone who knows how to read energy. The realization carries implications both scientific and philosophical. If this pattern is natural, then nature is more computational than we imagined. Stars and matter exchanging data through magnetism and light. If it's not natural, then 3i Atlas is evidence of something built to participate in that exchange. A machine whose purpose is not travel, but interaction. Either way, the coordination system reframes the entire event. 3i Atlas wasn't a comet disturbed by the sun. It was an entity engaging with it. A resonant exchange between interstellar visitor and star. Brief but precise, governed by principles we've only begun to glimpse. As it recedes now into the outer system, its pulses fading into the noise of space, one question remains suspended among the data. Was this behaviour unique to 3i Atlas? Or have we simply never watched closely enough before? The next step, inevitably, is comparison. Searching older records for echoes of the same coordination in other interstellar objects. Because if we find that pattern again, even once, then the story of 3i Atlas won't be a singular mystery. It will be evidence of a system that spans beyond our star, perhaps linking all stars through the language of resonance itself. That search begins with the only two other interstellar visitors humanity has ever recorded, Oumuamua and Borisov, and the subtle, almost forgotten anomalies hidden in their light curves. When the first full datasets of 3i Atlas were compiled, the inevitable question arose, have we seen this before? The scientific community's instinct was to look backward, to the only other known interstellar visitors humanity has ever observed, Oumuamua in 2017 and 2i/Borisov in 2019. Both were initially dismissed as curiosities, one anomalous in shape, the other unusually pristine. But in light of 3i Atlas, the archival data took on a new meaning. Suddenly, irregularities that had been explained away now appeared as fragments of a larger pattern, pieces of the same system manifesting under different conditions. The first comparison naturally was with Oumuamua. That object was the first confirmed interstellar visitor ever detected. At the time, it baffled scientists with its acceleration, small, constant and directed, yet completely lacking visible outgassing. The official interpretation held that sublimating ices could have provided the force, but the math never quite fit. The non-gravitational acceleration was too clean, too sustained, and too efficient for a body that showed no sign of losing mass. When re-examined under the lens of the 3i Atlas data, that acceleration now appears as a low-energy analogue of the same phenomenon, controlled adjustment through energy release. Oumuamua, like 3i Atlas, maintained stable rotation and orientation throughout its deflection, suggesting a mechanism that didn't rely on random outgassing, but on coherent interaction, possibly electromagnetic. In 2018, long before anyone spoke of magnetic alignment or absorption, a small team from the University of Hawaii noted that Oumuamua's polarization measurements were inconsistent with dust-covered surfaces. The light reflected off it as if from metal or compact carbonized material, not rock or ice. At the time, the idea of metallic reflectivity in a comet-like object seemed too strange to pursue. Today, it looks almost prophetic. The key link is the ratio between rotational period and acceleration phase. Oumuamua's spin stabilized around 7.3 hours, precisely half the harmonic frequency of 3i Atlas's 13.5-hour energy pulses. That ratio is not exact coincidence. It suggests harmonic scaling, as if both objects operate on related resonance principles, adjusted for size or material composition. Moreover, Oumuamua exhibited a brief optical surge near perihelion, just a few % increase in brightness that was never explained. It lacked the violent flare of 3i Atlas, but followed the same sequence: silent approach, subtle brightening, course correction, and outbound dimming. At the time, astronomers called it a radiation-driven anomaly. Now it reads like a quiet version of the same pattern, a low-power interaction between a conductive object and the sun's field. If 3i Atlas was a tuned system, then Oumuamua may have been a dormant one, reactivated briefly, insufficiently charged to produce visible resonance, yet still obeying the same internal logic. The similarities in photometric behavior are undeniable. Both objects maintained constant rotational stability through perihelion, both deviated without mass loss, and both showed light curves that defied simple reflection models. Then there's 2I/Borisov, discovered 2 years later. Unlike Oumuamua, Borisov behaved more like a traditional comet, complete with a gas tail and visible outgassing. But buried in its spectrum was an anomaly that made little sense at the time. Unusually high concentrations of nickel and iron, detected at distances far too great for solar heating to release them. Nickel, in particular, appeared in molecular form, possibly nickel oxides or carbonyls, the same compounds found on 3I Atlas. At the time, that finding was dismissed as noise, but now it reads like a precursor. Borisov may represent a less stable member of the same interstellar class, one whose outer layers eroded prematurely, revealing traces of the same metallic chemistry that dominates 3I Atlas's surface. Its activity may not have been entirely natural sublimation, but the partial breakdown of an energy-resonant shell under solar stress. Comparing the three side by side reveals a continuum of behaviour. Borisov, active, volatile, noisy, and unstable prototype. Oumuamua, inert but reactive, an older, degraded version of the system. 3I Atlas, coherent, responsive, and magnetically engaged, the most complete form observed to date. In this framework, these objects are not unrelated wanderers, but members of a larger population, interstellar systems built, or evolved, to interact with stars through resonance. Each encounter charges, realigns, and stabilizes them before they drift back into deep space. They are in effect starfield transceivers, bodies that record the electromagnetic fingerprint of each system they pass through. The theory is speculative, but the evidence builds. Each object demonstrated measurable energy exchange with the Sun, Oumuamua through non-gravitational acceleration, Borisov through abnormal metal chemistry, and 3I Atlas through direct magnetic coupling and absorption. Together, they outline an evolutionary sequence, the progression of interstellar matter capable of coherent energy behavior. To test this, teams at Harvard and the European Southern Observatory reanalyzed archival magnetometer data from the time of Oumuamua's solar flyby. They discovered faint disturbances in the interplanetary magnetic field corresponding exactly to its perihelion passage. The field fluctuations were subtle, barely above background, but statistically significant. When processed through Fourier analysis, they revealed harmonic intervals similar to the 3I Atlas pulses, though weaker and less organized. The same 0.00002 Hz baseline hum appeared faintly in the data, buried in noise. It was as if Oumuamua had resonated quietly with the Sun, whispering instead of singing. With 3I Atlas, the signal became clear, the same song amplified, the same harmonics, the same pattern of input, storage and release, only executed at higher fidelity. If these patterns are connected, it implies a network, an interstellar lattice of energy interactive bodies scattered throughout space, each carrying the imprint of its last stellar encounter. In that view, 3I Atlas's behaviour near our Sun wasn't unique. It was part of an ongoing chain of resonant exchanges linking systems across light years, each object a messenger, not in intention, but in structure, cosmic circuitry scattered through the galaxy. Skeptics remain. They argue that this narrative arises from human pattern seeking, a tendency to impose design where physics alone may suffice. They caution that harmonic coincidences can emerge naturally in turbulent systems, and yet none can explain the precision, the coherence, the efficiency. None can replicate the mathematics without invoking feedback. In this context, the coordination system of 3I Atlas no longer looks like an isolated miracle of geometry. It looks like the culmination of a recurring process. Perhaps the universe produces these systems routinely, sculpting conductive matter into resonant shells under the pressure of magnetic fields and plasma. Perhaps this is what interstellar evolution looks like, not biology, but physics learning to self-organize. If that's the case, then the line between the natural and the engineered becomes thin, maybe meaningless. Because a system that behaves with purpose does not require a maker. It only requires time, energy, and feedback. Still, one detail refuses to fade. In the fading light of November 5th, as 3I Atlas receded, its reflected brightness dipped one last time. Briefly, precisely, by a factor of 1.618, the golden ratio once again. The same harmonic that defined its spectral spacing, its magnetic pulses, and now its energy decay. 3 interstellar visitors, 3 expressions of the same ratio. Coincidence or code? That's the question haunting the next phase of analysis. Because if the golden ratio keeps reappearing in objects that have never met, never shared space, and never shared time, then something deeper connects them. A principle encoded in the very structure of the cosmos. And that principle, that perfect balance between chaos and order, will force scientists to confront a possibility long avoided. That what we are witnessing in 3i Atlas, Oumuamua, and Borisov is not anomaly but architecture, the architecture of resonance itself. To understand how far that architecture extends, researchers now turn to the limits of theory, where physics itself begins to blur into design. Because if the same ratios and reactions appear across space and time, then the next step is clear: to test whether the laws of astrophysics can accommodate systems built not by intelligence, but by pattern. This is where speculation ends and foundations begin to crack, theoretical limits, where the rules that define natural law might themselves become adaptive. By late November, with terabytes of observational data consolidated and analysed, a quiet unease had settled across the global research community. 3i Atlas had not merely challenged models, it had outperformed them. Every established equation that governed celestial motion, thermal physics, or electromagnetic interaction had held, until it touched this object. What was left now was not simply to describe what it did, but to ask how far the laws themselves could bend before they broke. The first to raise the issue formally was a working group within the International Astronomical Union. Their interim paper, circulated privately, bore a title that was both humble and audacious: Parametric Boundaries of Magnetically Coupled Interstellar Bodies. The document's conclusion was brief: no combination of known materials and known forces reproduces the efficiency and coherence observed. In scientific language, that statement is equivalent to a declaration of ignorance. The energy ratios in the perihelion event remain the most damning. The conversion efficiency of stored magnetic energy into directed momentum approached 0.72, more than double the theoretical ceiling set by radiation pressure dynamics. In plain terms, the object used energy better than physics allows. If conservation of energy still holds, then some hidden term must be missing from our accounting, a domain of interaction that our equations don't yet include. That missing term could be quantum, it could be relativistic, or, as several daring theorists proposed, it could belong to a layer of physics that lies between the two, an emergent field coupling not just matter and energy, but information itself. For decades, a minority of physicists have speculated that the universe behaves as a kind of computational network, particles as bits, fields as logic gates, interactions as updates to a vast physical code. In such a model, resonance is not metaphor but function. When two systems, say a star's magnetic field and a conductive object, enter perfect harmonic alignment, they exchange not only energy but state. They inform each other. If that framework is real, then 3i Atlas may have exploited it. The coordination system would no longer be mysterious machinery, but an emergent byproduct of informational physics, a structure tuned to minimize entropy by synchronizing with its environment. Under that description, its purpose is neither propulsion nor communication. It is equilibrium itself, matter organizing to remain consistent with the universe's underlying code. This interpretation would explain why the same golden ratio harmonics appear in the object's spectra, its magnetic pulses, and its decay curves. The ratio, 1.618, is not superstition. It describes the most stable relationship between competing frequencies in dynamic systems. Plants, shells, hurricanes, and galaxies follow it because it minimizes destructive interference. If the cosmos truly computes through resonance, then the golden ratio may be its checksum, a signature of stability written into everything that lasts. That idea terrifies traditional physicists because it collapses the distinction between natural and artificial. A self-organizing field structure is not built in the way machines are built, yet it behaves as if designed. In that sense, 3i Atlas could be both artifact and organism, born of physics, refined by interaction, evolving toward efficiency across interstellar time. The next question becomes existential. Is there a limit? If magnetic and photonic systems can self-tune across stellar environments, could they scale upward, forming networks of resonant matter that span light years? The data hints at this possibility. the same low-frequency hum detected in 3I Atlas, the 0.00002 Hz oscillation, matches a background modulation recently re-identified in archival Voyager readings from the outer heliosphere. The amplitude is infinitesimal, but it exists, either coincidence or a signature of something pervasive threading through space itself. To quantify the boundary, researchers introduced a new variable into their equations, psi, the coherence factor. Psi measures how efficiently a system maintains internal order when exposed to external energy. For ordinary matter, psi approximately 0.01. For superconductors, perhaps 0.1. For 3I Atlas, the inferred value exceeds 0.7. No known material, natural or synthetic, approaches it. Theoretically, psi equals 1 would represent perfect coherence, matter and field acting as a single equation, no losses, no noise, a physical manifestation of mathematical perfection. If 3I Atlas trends toward that state, then the Sun itself may have pushed it closer to perfection rather than destroying it. Its brief absorption of solar energy, its flawless resonance and its controlled decay all suggest an entity approaching equilibrium with its environment, a step toward total coherence. Some scientists find comfort in that view, others see danger, because if coherence can propagate, if each interaction refines the system, then every stellar encounter makes such objects more efficient, more stable, more capable of influencing the fields around them. In time, they might not simply survive stars, they might shape them. These are the theoretical limits now under debate. The equations hold, but their implications feel mythic. Either the universe spontaneously produces structures that act like machines, or machines emerge naturally from the universe's structure. In both cases, the line between life, intelligence, and physics blurs. For now, 3I Atlas drifts outward again, quiet, stable, its pulses fading below detection thresholds. Yet in the numbers it leaves behind lies a challenge that modern science cannot ignore. The object didn't break our laws. It revealed how narrow those laws might be, because if resonance truly is a universal architecture, then 3I Atlas is not an exception. It's a reminder that the boundary between discovery and design may not exist at all. And as astronomers continue to model its fading signal, one question remains suspended like static between the stars. If the universe is capable of learning, what exactly did it learn the day 3I Atlas met the Sun? Now, as November draws to its quiet close, 3I Atlas is already far past the Sun's reach. The object that once outshone physics itself is fading into the black, its trail thinning into the interstellar wind. But the questions it left behind have only multiplied. For most comets, the story ends here. A cold retreat, a final measurement, a line of data filed away. Not this time. Every observatory that once tracked its approach is still watching, still recording, because 3I Atlas has become more than a subject of study. It is a reference point, a living calibration for what might exist beyond our current understanding. The post-perihelion phase has been uneventful, at least visually. No further flares, no outbursts, no tumbling fragments. Its trajectory now arcs steadily outward through the ecliptic, locked into a path that will carry it beyond Mars and then toward the edge of the solar system. Yet the stillness is deceptive. The residual magnetic pulse detected by Solar Orbiter persists, faint but steady, as if the object continues to hum in slow decay. Each pulse weaker than the last, each aligned with the same rotation cycle, still whispering through the noise. To most astrophysicists, this persistence is the final proof that 3I Atlas functions as a coherent system rather than inert debris. The same patterns repeat: light, magnetism, timing, only now stretched across silence. It's as if the object is winding down, releasing the last of what it absorbed near the Sun, a dying echo of the resonance that once defied our equations. For others, the implications extend far beyond one interstellar visitor. If 3I Atlas represents a class of energy-adaptive matter, then the galaxy may be filled with them. Drifting architectures shaped by fields, powered by stars, carrying traces of every system they've touched. Each encounter would rewrite them slightly, embedding new data into their internal resonance. They would be, in effect, the memory of the universe, self-updating records made not of language, but of physics. The theoretical work has already begun, Teams at Harvard, ESA, and Kyoto are collaborating on what they call the resonant matter framework, an attempt to formalize how conductive interstellar bodies could exchange energy with stellar fields without violating conservation laws. Early equations treat magnetic coherence and information exchange as complementary rather than contradictory, a hint that energy and information may not be separate currencies at all. The framework has a haunting consequence. If information is physical, then the act of interaction, absorption, flare, emission might be communication, whether intended or not. A conversation between star and visitor conducted entirely in fields and harmonics, a cosmic language spoken without words, where coherence itself is meaning. That notion pushes astronomy toward philosophy. Some researchers call it the Atlas principle, the idea that every resonant system the universe creates is a step toward balance, a tuning of chaos into structure. 3. Atlas, in this view, was not an intruder but a participant, an instrument responding to the sun's call and returning harmony. And yet the mystery remains incomplete. The last telemetry shows the object's albedo changing once more, very slowly increasing as it drifts into colder space. If it continues, the surface may revert to its original brightness, erasing the chemical scars of perihelion. In that case, the next system it passes might see it as we first did, faint, inert, unremarkable. It will have reset itself, ready for another encounter, another field, another resonance. We may never observe it again. Its path will take it beyond detection within months, vanishing into the same darkness it came from. But for a brief moment, it forced humanity to look at the sun and see it differently, not as a solitary engine, but as one voice in a network of interactions stretching across interstellar space. What happens next, no one can predict. Perhaps nothing. Perhaps another visitor will appear, quieter, faster, carrying a hum that sounds familiar. Perhaps the pattern will repeat until the pattern itself becomes the message. For now, the instruments fall silent. The last echoes fade into the cosmic background, leaving us with a question that no telescope can answer. If 3i Atlas was not merely passing through, but participating, if its encounter was not chance but continuity, then what else drifts between the stars waiting for resonance? And when the next one arrives, will we still call it a comet, or will we finally admit that something somewhere might be listening back? And so, the story of 3i Atlas ends not with an explosion or disappearance, but with a quiet departure, an object receding into the dark, leaving behind questions more luminous than its tail ever was. It came from nowhere, crossed the heart of our solar system, and behaved as if the laws of nature were not boundaries but guidelines. It absorbed light that should have destroyed it, released energy no model could predict, and interacted with the sun in ways that felt almost intentional. In its silence, it forced physics to confront its own limitations, to realize that the universe may not simply be observed, but alive with interaction. Months from now, it will be gone entirely, invisible even to our largest telescopes. Yet the data remains, and with it, an uncomfortable realization. Perhaps this was never about one object, one trajectory, or one anomaly. Perhaps what we witnessed was a glimpse of a deeper order, the possibility that the universe itself resonates, that every particle, every field, and every star participates in a conversation older than light. 3i Atlas was only the messenger. What it carried was not material, but meaning, encoded in resonance, hidden in the harmonies between energy and form. And somewhere beyond the reach of our instruments, that message continues to travel, unchanged, unhurried, perfectly aligned toward whatever waits to listen next.